a Google session, but he's going to be talking about deductive databases.
Thank you, Ben. Let me quickly get set up. Shall we wait for the planned scheduled time, or shall we? 26 seconds. Oh, okay, great. Well. All right then. Let's talk about deductive databases. So, who knows what a mangle is? A mangle is this old-fashioned device that people used to use before there were washing machines. So they washed laundry in buckets of water, and then they rinsed it, and then in order to get the water out and have a like ironing effect, they put it through these two rollers, and there's like this crank, so it was a hand-operated machine. And I'll tell you a story, and it's the story of centered around deductive databases, that is around cleaning data, right? There's some analogy here, and it plays on many levels. So we zoom out from the very concrete sort of imperative programming style to a more declarative paradigm. But before we do that, I want to start from a very high level, right? Like a long time ago, Peter Nauer wrote this essay that is programming as theory building, where like in the light of recent industry trends, it's like helpful to remember that there is an alternative view to the predominant and often repeated view that programming is about producing artifacts. So many people believe that writing software is about writing code or documents or things like that. And but there are several things that actually aren't really captured by that. And that is something that is not so obvious often, and it often gets rediscovered. But it's like programming as producing artifacts doesn't really capture many things. So in his essay, Peter Nauer wrote about this, that like the theory of a program is what he advances. Theory here means not like a formal theory, not like Greek letters and horizontal bars, but it's what people understand. Like why are the abstractions written that way? Why have the trade-offs been done like that? And why is the program the way it is? Like what has produced these artifacts? And he's writing about this knowledge being essentially in people's heads. And it so happens that when the team gets disbanded and the software is still used, that the software is dead, right? It's no longer alive, right? Like, and it can be revived by people going there and understanding again and reconstructing the motivations and the thoughts that went into the software. And that, in my experience, that explains a whole lot more what makes systems successful, what makes teams successful, and what makes software really alive. You know, I have some random diagrams here that are supposed to convey that the modern, as time passed since 1985, things have got more and more complex. So there's a lot more things to understand, and you have to work with a lot more people, and you have there are a lot more layers that one has to keep in one's head. And it would be really nice if that knowledge and understanding was not in people's heads, but that we could actually make that explicit and easier to grasp. So I want to zoom in now back to the more to the topic of this talk, which is about databases and data modeling. So data modeling is one place where the model and where these decisions sort of manifest. Like when we make our data structures, we make some decisions and they end up being the way it is through some thinking. And we don't see the thinking, we see the data structures, right? Or we see the schema definitions, and the database has a bunch of tables. And for a while, all of that is fine, but at some point, software needs to evolve, right? Something changes. There's new kinds of data, or the existing data is different. Especially if it's a successful system that is operating for years, then things are going to change in the world, and you'll have to want to change your data definitions. And what then happens is that in order to change systems and involve them in an incremental way, you need to change a whole bunch of stuff. You don't just change the schema and things carry on. You need to understand the entire rest of the program and how things hang together and sort of like pipe through the data all the way through the stack in order to make the system evolve to handle this new kind of data. And with respect to static checking, that's very interesting, right? Because on the one hand, we like schema definitions, we like type definitions, but at the time that these forces come that require making a change to these layers, then suddenly these things get in the way, because like we are able to evolve our model and understanding of the world. We're like, I can do it like this and I can adapt that. But we have to go through the bureaucracy and changing all the type definitions in the program. So that's a very clear indication that our mental models sometimes can be advanced and sort of further on than what is in the code, and that makes these changes kind of difficult. So that brings me to Mangle Datalog. Mangle Datalog is an open source project. It was born in the context of an actual project that later on, so it was a prototype to in the cybersecurity context. We wanted to visualize metadata that talks about log processing pipelines, but I'm not going to talk an awful lot about that. The key point is we didn't know what data models we would have. We knew that there would be data models, but the data models didn't yet exist, so we wanted to prototype anyway, because this was essentially like a joint 20% project of a number of very talented engineers that I'd like to acknowledge their work. That's not about the data log, but about the front ends that showed these things, which was internally recognized, and it's used by hundreds of people every day. So it was very successful. And I think, I'd like to think that our approach to data was part of this success. And that's why I think it's worth that everyone should know about this, and everyone should could benefit and replicate this approach to data outside of this particular project. But for that, you need to know Datalog. So who knows Datalog? All right, so many people know Datalog, that is great. So I've added a few slides to sort of like show the gist of it, but so most of you already know this stuff. Datalog has you know that Datalog has seen quite the resurgence, so it gets essentially rediscovered every year or every couple of years, and the frequency at which it gets rediscovered is sort of increasing, right? Like because Datalog actually comes out of as you know, right? You said you know, like the Prolog, out of the Prolog, a subset of Prolog, like being applied to data operations, but it's so much more than that, right? So briefly, we can model our facts. Our facts are like, like a, as if I had a subject, predicate, object structure. But or as if I took my relational tables and I took the table name and I prefixed that, and I get these tuples. So essentially our facts are tuples with a name attached to them. And Mangle Datalog adds structured data. This has also been done many times, like to add data structures that are more than just basic atomic types. You can actually have lists and records and those kind of things, maps. And that helps meeting the data where it is. So we can write up data. Then come the rules, right? I'm not going to dwell on this a lot, but you know that if you have facts, you can also have atoms, which are like a predicate applied not just to basic data types, but they can have variables. If you have variables, you can define matching, and if you can define matching, you can define what a rule is. So a rule takes one of two forms. Either it just states a fact. Can you see my pointer? Yes. So this one just says this fact is true, and then we have declared this tuple. We have summoned this tuple into existence, and that alone, by the way, is very useful, right? Like if you think of configuration files, there's many situations in programming where you just want to state the data literally, and many programming languages don't do that. You can build up objects, or you can like put some numbers there, but structured, checked data definitions are not a thing. Like people send around JSON or something like that. That is not what we want. We would like to have static checking, and we would like to sort of take data seriously. And then come the second form of the rules where you have the right-hand side. it reads from right to left, right? Like, so if all the goals on the right-hand side match, then you create a new fact that is specified on the left-hand side. So in the example, we have like some facts, and then we can make a rule that says, like, if I have an author fact and I have a book fact, and then here I have like the R is matching this record here, and then I can like match the fields. If all of that is true, then I can just simply extract the information in these facts into a new fact, which is called author here and title. So this is like an interesting, the interesting thing is now that this rule, right, like it's at the same time it's a transformation. We take data in one form, we turn it into another form. But so in transformation, we would think of it as a process, right, as a program that gets executed, but it's also declarative, right? Like it doesn't really say which of these things we consult before. Do we first look into the author table, or do we first look into the book table? There is some implicit dependency, right? We need this R here in order to extract the fields out of it. But which of these let's say, tables we query, that is not in there. And that is the real power of this paradigm, right? Like that is declarative. It leaves open how we want to execute this, and that gives us the possibility to execute things in a different way. For example, to apply database optimizations. But we'll get to that in a second. So then this very declarative style, it kind of makes us, it enables us to give the definition, like the semantics of data log in very few words, right? We just say the semantics of a data log program is the fixed point computation, right? It's like we start with the naive algorithm, starts with the initial facts, and then it iterates the rules. And you can see from the movement of my hand that this is a little bit like pulling the crank on the angle, and we get our data into the form we want. We do not need to really care about the order in which rules are applied, and whether they are represented in memory or on disk, or what happens, like how. It just is a very abstract, high-level description of what we want. And the names for this, right, the extensional DB is like the things often you start with a given amount of facts, which is maybe your existing configuration files or database tables or things that were declared inline. And then the rules turn this database into a larger database that has more facts. So this again to highlight, right, this very high-level spec. This is an operational semantics, right? But it's not really about the algorithm. What matters is the result of the algorithm, and we can get to the same result in a different way. And just a brief, it needs to be said. Like I've said it, like for historical reasons. Like we see data log as a subset of Prolog, but maybe that's the wrong perspective, right? Like maybe the data log is actually the thing that is more fundamental, more widely applicable, more useful as the basis for extension in all sorts of things than Prolog ever will be. Because Prolog is a full programming language. It specifies that there has to be top-down resolution. Of course, it's Turing complete. You can do a lot of stuff. But the real shortcomings of Prolog from an abstract point of view is that the negation in Prolog is not logical, right? Negation is actually imposing an order, so that gives all sorts of problems. So if you write your goals in a slightly different way, your program may not terminate because you have to really know the order in which the rules are evaluated, and that makes it terrible. So some folks like Girard famously said that he finds Prolog vulgar, right? That it's a vulgar programming language, that it's not logic. And this is the point, right? Like in logic, this is not, there has to be a clear meaning. And in data log, we'll get to it, there's a very easy way to define negation, and it's very easy to understand, and no one will object to this. And then this what I mentioned earlier, right? Like we call this top-down or bottom-up evaluation, or they used to call this forward chaining or backward chaining in artificial intelligence, right? Like whether you start from a given end goal, like, and then you go and check the rules whether it is possible to derive this. This is top-down evaluation. Or bottom-up is like what I specified earlier. You start from a given set of facts and then you derive all consequences. And the special thing about bottom-up evaluation is that all the theory that went into database optimization applies here, right? Like you can have hash joins, you can sort of like do batch processing of large things ahead of time, and that enables like a lot of efficient ways of computing the consequence of the facts, which in Prolog is often available as an implementation detail, but it's not really, like it's a property of the Prolog implementation whether it gives you that, whereas in Datalog this is, we are free to do this as part of that declarative nature. So then I promised I would talk about negation. So negation, right, like we can take our program and we can split it and say like a negated atom is a very useful query. It says I tried to find something in this table and I couldn't. That's a very easy semantics. It's not controversial at all. But for that, the table has to be fully computed. So I can take if I can take a Datalog program and I can sort of logically separate it into slices, then after a slice is fully computed, there's the database, and then if the result is in the database, then the negated atom will fail, right? You won't be able to match it. But if it is not in the database, then the negated atom will match. And this is called stratification, and stratification is really easy to understand. I'll briefly mention that now what's so attractive about Datalog is that, like in recent years, many people talk about knowledge graphs, right? Like about like semantics, like you want to represent facts about the world in an arbitrary, extensible manner. Then graphs are very nice for that. But the problem with most approaches to knowledge graph, or if anyone remembers the semantic web, right, is that all those graphs are binary. But here we have arbitrary relations, right? We can have n things lined up in a tuple, and we can express very powerful interconnections that way. And Datalog supports recursion out of the box, so you can have transitive queries. You know all of this, right? Like, but that together means you can impose a graph view on sort of the things, no matter how you model them. And that is very powerful, and sort of across the stack, it's possible to, through articulating these rules, like have very, very powerful views on the same data. I won't go too much into the examples of static analysis, but of course Datalog is a way to teach static analysis, right? The simple classic data flow analyses that happen in compilers are easily expressed in Datalog. Here's the example of live variables, right? Like there's like definitions and there's uses, and the information flows backwards, right? Like so if I have a graph, which is a control flow graph, and some of the nodes, they can declare variables and some use variables, I can say which blocks define and use variables. And if I have a use, well, the variable is live. And if a variable is live in a successor, so this is a successor, right? Like this edge, these two facts together say that the variable is live in a successor, and my current block does not define the variable, then it's also live in this block. So that kind of expresses that this flows backwards. And if you know the Dragon book, right, like its more recent edition actually has a nice chapter on Datalog. So it's kind of slowly permeating sort of the world that maybe Datalog is a better way to think about these things, an easier and much more direct way to express logical facts about graphs, and we can use these things for static analysis. And a recent example is the Polonius model for the Rust borrow checker. I have to say it's not a complete explanation of the borrow checker, but it does express the rules, right? So the compiler is accumulating a bunch of information about variables and about the kind of conditions that they have on regions of memory. But we can feed this information into Datalog rules, and then the Datalog rules will be checked at every program point. It will check that the information is sort of consistent, and if there's no error, then we know that there are no borrow checking problems. And that's, again, right, like we were talking about the theory of a program, right, like about like the understanding. We can capture the understanding of what borrow checking is by simple rules, and that is a very powerful approach. Now when I talk about Mangle, that was all Datalog, right? There was no Mangle yet in all of this, except maybe the structured data. So there's a lot of things I could that are in Mangle that you know, like we want to have because there's a lot of things that the modern programming languages should bring. So there's a module system and things like that. But I just want to highlight the key idea. The key idea is that in Datalog is of course very restricted. So all you can do is these fact consequences, but from time to time it would be really nice to do some transformations that are maybe no longer declarative. Like, so you want to essentially generalize the paradigm to be able to do more programming. And a lot of the publications of recent years that use Datalog as a basis of programming language, they do this, right? It's all about using this very expressive paradigm in the context of a general purpose programming language. Well, we start differently. Like I was talking about taking a program and slicing it into these layers. What if we, not before or after or around the fixed point computation, but in the middle of the fixed point computation, at these points where we logically fully computed our relations, what if after those things we inserted a bit of general purpose computation, and then we let the next stage of the Datalog program continue and do its fixed point computation? How far can we get with that, and what kind of expressivity does that buy us? And to my knowledge, so I've read a few papers. To my knowledge, I haven't seen an approach like this, but there have been many approaches that took Datalog, so I would not be surprised if somebody had done that sort of 10 years ago or 20 years ago. So it's really been around for a long time, but it has been working for us, and I'm going to show some examples. So the easiest example is aggregation, right? Like people use SQL for databases, and SQL is not just relational calculus, it also adds aggregation. So for aggregation, you fully compute some table, and then you have a sort of result relation that has like everything. And now you want to fold over that, right? You want to summarize things. Like in this example, we have a project, and it has assigned some developers with some hours, and if I want to sum up all the hours like I want to know how many developers are on a project and how many hours in total are assigned, like I can express that like this. So this same idea of like first a Datalog program is evaluated, it produces some intermediary result, and then we can run this aggregation on that. Like that, I find it's even though it's no longer pure Datalog, it's very easy to understand how it blends with the rest. And maybe the syntax takes a bit of time to get used to, but I guess it's still better than the SQL syntax. This is, by the way, very related to how MapReduce works, right? Like you first compute a large result relation, and then you group the keys that are processed together, and then the reduction phase like turns the list of results that are for one key into a summary. And this thing after the pipe operator essentially says how to summarize. So that's one example, right? We've taken Datalog, very simple, and we've extended it, and still we have these termination properties, right? Like we don't need to care about the order in which if there were multiple goals, right? We wouldn't care about the order in which they are written. We don't really have to care about, what comes first. We still declaratively specified what's supposed to happen. Next thing is functions. So if you just add functions to Datalog, then most of these properties like break. Like then Datalog no longer is Datalog, and for example, you can have this non-termination, right? You can say I have a piano fact, which is like a 0, and then I just add successors, and this will just not produce any fixed point, because in every iteration, like however you want to evaluate it, like this thing says just iterate and iterate and iterate, and there's no end to it. So that is obviously not the way to go. I mean, if you do this, you really have to know what you're doing, and you're back to full programming. You have to know something about the control flow and sort of like how many of these facts you have generated. You have generated too many facts, essentially. So that's the question. And could we actually find ways to add functions, like things that generate new forms of data, new facts, but still, like knowing that we're in the middle of this fixed point computation, still do that in a way that preserves some of the declarative nature, and that still guarantees termination. So one example we have is the custom lattice join. So you could kind of say, you know, like these rules, they generate facts, and then we have these sets of facts, and if we have more, like there's a natural join, like a lattice join operation is just to make the union of them. But what if I don't want all the tuples? What if I find a good fact or a better fact, I want to remove like the old fact? And that's like as if we would define a lattice with a custom join operation, where the easy example is the shortest paths, right? Shortest path is not something you can express in data log, but you can express in mangles. So essentially, you have, you know, you either have an edge or you extend an existing shortest path with an edge. But if you then found a path, if you found two paths that are the same, they have the same start and end point, and you find that one of them is shorter, just pick the one. And the way we do this is like so this is one example of things that are very expressive that you can insert into this data log computation. And it will not jeopardize termination. If the original thing terminates but had too many tuples, the updated thing will also terminate, and it will have less tuples and will be more efficient. So the way we declare this is to say, hey, there's this merge predicate, and after we've computed the like one iteration of the iterative fixed point computation, we will actually go and call these things and then have like the tuples. We will call this merge predicate. So it's like a computation inside the computation where we check what are the lengths of these paths, and can we actually, if we can call this and this predicate produces a shorter fact, that's a signal for us to say, okay, we can delete the other one. And the implementation will actually delete the tuple. Yes, question?
Couldn't this lead to non-monotonic reasoning if you are able to remove a fact from the database? So say I later query exactly whether or not a longer path exists, but we've used this mechanism to remove that longer path and the shorter path existed. Doesn't that kind of violate the declarative property that you want from data log?
Yes, absolutely. And the reason this works here is that we don't actually go and update. It's not as if like the entire thing is considered, right? We produce a new iteration in the iterative fixed point computation. Then we check for the new things. We check whether there are existing things. So there's like we don't go and delete. But yes, like you cannot decide for rules whether they are non-monotonic, and it's so in this case it works, and we don't really like this custom lattice join is very restrictive in a sense. So I don't think you could get into this, but of course in general you cannot. There's no way to decide the monotonicity of the rules. So if you had a more general way to do this, then you could write these non-monotonic programs. Like I think in Soufflé is the same trouble. So I believe in this case we would be monotonic because after the iteration is done, the existing stuff prevails. But like maybe for other more general ways of doing these custom lattice joins, we might get into this problem. But I don't think we support them right now. Getting back to how to handle data, like a general approach to handle data, right? Like this syntax of having facts, like with maybe some input and some output predicates, that is also that's a very uniform way to access any source of data. And you could imagine any sort of computation or querying external data sources to take the very same syntax. So there's an external predicates API where we could like say, okay, we make an RPC to some backend, and we give it these input things, and then back come these output variables, and that can be then configured through mode declarations. But apart from external backends, I mean, you could really think of any sort of computation that you can expose as these kind of tuples. You can express them with the same syntax. Of course, then, like there is this, what I mentioned earlier, there's some dependencies, right? With mode declaration says some of your inputs have to be there before. So while it's true that the order doesn't matter, if you declare something as having an input mode, that means, okay, like some other goals have to happen first so that I have all the inputs, and only then I can actually run this external predicate, let's say, and produce the output variables. So as I said, there is an actual system that works this way, and this uniformity, it goes a long way, right? Like, so we had we found a need to have these data log evaluations at build time, because there's static information, there's like configuration files, or there's like stuff that the build system knows. We pull the crank, we evaluate, and we get our facts. Then we push these facts into our production environment, where there's like more data available, right? Like, so we evaluate again, and we access external data, and we get more facts. And because that's not enough, right? Our users may have other ideas of what things they want to query for. We also let them write queries, which are data log programs, and then we sort of incrementally taking the existing intentional database as a new baseline, right? Like we pull the crank again, and we do another data evaluation, and we return the results that the user requested. So this, I don't have a name for this, you know, I'm happy to take suggestions, but the fact that the same sort of kind of computation happens across all the layers in different environments, this is something that you don't find all that much, right? Like in a traditional three-tier application, right? Like the database does something, and then the middle layer does something, and then on the front end things happen, but they're all different. They use different languages, they use different patterns, they use different abstractions, and it's very annoying because that is what is difficult to change, right? That requires knowing many different things if you want to go across the whole stack, whereas this one is the same thing across the stack, the very same thing, and it's very flexible. And we have a form of static checking that I didn't go into. So what does static checking mean in Mangle data log? So it means that we can, through type information, sort of like tell if you wrote a query that can't return any results, we tell you, right? You probably have made a mistake. I briefly want to zoom out again and see how this could apply to cybersecurity. This is not the system that is implemented, but it was the thing that led me to investigating query languages. And let's see what you think of this. So in cybersecurity, you have to deal with information and event management. It really starts with knowing what you are protecting, actually. What is protected, what is worthy of protection, what is actually happening. And so people write these log processing systems, and they essentially take the non-contextual information and they try to curate and select and add sort of annotate and enrich information, which can take many forms. Like you can have classification, but the forms can also, they can be false positives and all sorts of things, right? And there can be legitimately different ways to use the same, to view the same data. And to have a system that supports that, right? Like with data log, it becomes very easy because you just define facts. And these facts could come from the logs. You presented the logs in this view where the relevant things are. It could also be abstractions, right? That maybe there's like rules that produce these facts. We don't need to know. We can talk about these things like in a very abstract way. And we can talk about the patterns in an abstract way, right? Like we can define sort of patterns that we want to recognize by using the very same rule mechanism to express time series patterns, or like a privilege escalation, which is like when a process starts, when the parent process was not an admin, the child process was an admin had admin privileges. That is, you know, then apparently there's something going on here which is worth checking. And finally, we can compose the rules, and that is really something you should take away, right? Like data log allows you to compose queries, which you know, other query mechanisms and formalisms don't do. And so like everything comes together. If out of little building blocks we can build ever more building blocks, and it's all explicit. Like you can just look at the rules, and without knowing sort of, you know, what is going on in detail, like maybe this is a rule, maybe this is a log, right? Maybe it's an intermediary stored snapshot from last week. You can build like whole systems out of, and that's a way to tame the complexity. So to summarize, like what have we done actually here, right? Like I'm sure there are many ways, there are going to be many more languages based on data log. We have, like what I've wanted to highlight is that the declarative paradigm helps us to make things explicit, right? We can look at these rules, and the rules give us abstraction, right? We do not need to know. If we don't want to know, we do not need to know whether an atom on the right-hand side of a rule, where it actually comes from. But if we want to know, we can go and we can look up whether there are rules or whether it's an external thing, and we can drill deeper, but we don't have to, right? Like which is different in an imperative program with many data structures and mutation. So the uniformity has helped us, like give us maximal extensibility, right? Like it's extensibility with respect to data. You can add new forms of data. You can add new forms of rules. You can test your rules, right? Like, and you didn't necessarily need to know all this stuff ahead of time, as we didn't know our data model when we started. We were just able to change it along the way. And finally, like there are things, this expressivity that with few symbols you can express a lot of things, and the modularity that you can have things like packages and imports, which I didn't show. These things matter to humans, right? Like it's like many people talk about sort of like code being generated by generative AI and whatnot. But ultimately, if you want to be responsible for something, you need to be able to understand it, and you need to be able to understand it quickly. And then all these things that you know, like this hard-earned knowledge of programming languages, that modularity and good abstractions and good APIs matter. All these things are still true, and we need, like in my opinion, we need approaches like this that really focus on the data, right? Like not just on the computation, but how we do this with data definitions. That was what I wanted to show, and in our case, it worked very well. And I hope that you'll be able to use this in your own systems to maybe replicate and use a bit of data log to make the world a better place.
We do have time for maybe one or two questions real quickly.
Thank you. As you know, I'm a big fan of Datalog, and I'm using Soufflé currently. So I saw the operator that you want to add about for lattices, and Soufflé, yeah, the semi-join. Yes. So Soufflé has the subsumption construct that does something similar, but it's very nice and expressive, but there are two things with it. One is it complicates implementation, but let's leave that aside. We also have never used it fruitfully. It slows down like normal computation quite a bit, at least by a factor of 2, because every rule that might have results being subsumed needs to check before it produces new results. So do you have any ideas of how we can actually do something like custom lattices with virtually zero overhead?
That's an implementation question. I didn't expect those, but it's so the question was you were on the microphone, right? Like to repeat my understanding of the question, how to actually make this fast, right? Like have this expressive way of dealing with the mutations to the set of tuples you want to compute while not spending too much overhead. I think the key here in our system, so our system is very simple, right? Like we do all sorts of stuff in memory. In memory, things get very easy because memory is fast. But even so, like we had to tackle performance issues, and there are small things that make a big difference, right? Which is like indexing, just like in databases. So if you're gonna to check whether your subsumption holds, right? Like you're gonna make some computation. To make that computation fast, I mean, maybe you want to do other lookups and whatnot. If those lookups are fast, then the subsumption can be faster. So it's not a fundamental algorithmic answer, but it's just sort of like the constant overhead that is a big deal, right? Like by using the right representation and using the right index, querying the right columns, like we were able to find like big speed ups, and they were enough for us. If you ask me about the algorithmics, I don't really have a great answer for you. I think the thing I'm working on a Rust implementation of this, which is supposed to be more than just in memory, so it should actually go to disk and or to you know, like more scalable media for intermediary results. And I think the key is going to be as you get more and more facts, right? Like how you organize your data. Like a columnar representation, for example, will mean that you know, you can do your batch computation differently. So I think you still have to do the amount of work. You have to find the tuples that are relevant, right? But for example, like souffle has the equivalence relation. I guess that's a good example. If you know that your relation is symmetric, transitive, and reflexive, why don't you make a data structure that actually represents those things efficiently? And I know from my colleagues who use souffle that souffle is not great at sort of bring your own data structure things. In Mangle, there's a fact store interface, you can just implement it. So if you have an equivalence relation, like you can actually build a fact store that will respond to queries like very quickly, and maybe it's backed up by a union find algorithm, and that way, like you can, that can have a major impact on the sort of the complexity, because you have to do less work. It's no longer linear scans, but maybe, you know, you have like a reduction and you have log complexity to find your things. And I believe that's the key, right? So there's that sort of extensibility where you can choose how to represent your relations. I haven't thought much about how to represent the lookups for the custom lattice joint, but I suspect one could do something like this, where by making that configurable, you know your domain problem and you will be able to pick the implementation that works best. So that would be my answer.
Okay, so this concludes the session. So we'll see you after lunch, but let's thank the speaker.
We have two talks, and the first one is Sam, who's going to talk about the VM for verse. So maybe some of you remember the last year we had Leonard, who gave us an introduction to the verse language. So now we have information about how the VM for that language looks like. Sam.
Cool, thanks. I'll give you another introduction on verse shortly. Is that better?
I'm turning it down as we speak.
How about that? Good, yeah? You can hear me? Cool. So I'm Sam. I'm a director of language engineering at Epic Games. I manage a team of people working on creating VM for the verse language. So today I'll give a quick overview of the verse programming language, and then I'm going to talk about two projects my team has been working on for 2 years and 2.5 years for the other one. New bespoke VM for verse, so we're creating entirely new VM for running verse, and we're also creating AutoRTFM, which is a project for bringing software transactional memory to C++ code, so it's both a compiler and runtime. I encourage you to interrupt me in the middle of this talk. Don't wait till the end to ask me questions. So let's talk about verse. So verse actually is a programming language created by Tim Sweeney. Tim Sweeney's the founder and CEO of Epic Games. And when you hear Tim talk about verse, he created verse as sort of a programming language for what he describes as the metaverse. And when you hear him talk about that, he'll sort of describe it as a programming language for a shared open world 3D simulation. The way I like to conceptualize the programming model for verse is as if it's running on one massive computer with one shared heap. So everybody's code is running on the same heap, and code is running sequentially on a single thread. This is, of course, as if how it's running. This is not actually a scalable way of implementing verse. And the unit of execution on this massive computer is a transaction. Today, we have shipped verse to the public. It's a much smaller subset of the fully realized language we want. But today we have Unreal Editor for Fortnite. This is a tool that non-Epic developers can use to create islands on Fortnite. So when you go and play Fortnite, you can play Epic created games like Battle Royale. You can also play games not created by us. And those games are programmed in verse. So verse is multi-paradigm, so it's strongly typed. There's actually a lot of really interesting aspects to verse's type system. Sorry, I'm not going to be talking at all about verse's type system, but if you want to talk to me about that afterwards or talk to these gentlemen about that afterwards, please do. Verse has a really powerful functional subset to the language. It also has an effect system that lets you guarantee that you're running within that functional subset. There are aspects of logic programming to verse. It has unification variables. There's what we call lenient execution in verse, which is programs can run out of order. So unlike lazy evaluation, all of your program runs, but the order in which it runs is sort of determined dynamically based on values being available to the runtime. And there's object-oriented programming in verse, so there's classes, there's interfaces, there's inheritance, nominal subtyping. There's also a really powerful imperative subset, so you have pointers, you can read from those pointers, write to those pointers. And you also have transactions. So the unit of execution in verse is a transaction. Leniency and transactions are where I'm going to focus the main two parts of my talk today. So let's go through learning verse quickly. I'm going to skip over a lot of details, but this will give you an idea of sort of what the language looks like. So here we have variable x. It's immutable. It's unified with the value of 42. And when we print it, we print 42. That's pretty simple. You also have arrays in verse. Here we're defining an array with 2 elements, 42 and 666. And you can access the array using this subscript notation. So when you print the first element in the array, you print 42. When you print the second element, you print 666. This is pretty straightforward. Of course, you have expressions. So here we're unifying the variable y with 2 times x, and then you get the expected value when you print y. And of course, you can have functions. So here we're defining a function f, takes a single parameter x, which is of type int, and then function f also returns int. So it takes x as input, multiplies x by 2, returns that value. So then you can define y and unify it with the value f applied to 42, and similar to this, prints 84 as well. You can have classes inverse. So here we have a class named foo. It has 2 fields. The first field is a, which has a type int, and it has a default value of 42. And then you have a second field, f, which is a function. That function takes 1 input, returns also an int as output, and it adds the field a to the function parameter b. On the next line, we're defining x to be a foo. So we have x, which is an instance of foo, and the right-hand side of that unification is what we call archetype instantiation inverse. So the braces form an archetype. That archetype provides a value for a. Then we invoke the f function field on foo, passing it 1, so we add 1 to 666.
Could you also change the add?
Yeah, you can. Yeah, so that sort of traditionally is on a per instance, you can overwrite methods. Yeah. So verse has a really nice for loop semantics. So for loop inverse is really map. So here we have that same X array from a previous slide. We're iterating over every element of X, binding it to the variable E, and the body of the for loop actually produces the result E plus 1, and the entire for loop expression produces sort of this mapping of element in X to element in X plus 1. So you see that the array produced by Y is the same as the array produced by X, except every element has 1 added to it. Verse also has stackful coroutines. So here there's a primitive in verse called spawn that lets you spawn a coroutine that's not parented to any other coroutine. There's other primitives related to coroutines that I'm not going to go into. This my coroutine function, it defines a variable x, and then it calls into an API function called sleep. Here, when you call sleep with 0, actually what the game engine's doing is it's going to run this function again. It will resume this function after the next frame of the game engine begins. So yeah, stackful coroutines, they exist in verse. And you have mutability. So here we're defining a var x of type int. So really the way to read this is x is a pointer. We allocate a box for the value 42. We can read from that pointer. So we print 42, we can mutate, so we can write to that pointer, setting x to 666, and then we can print it again. Verse also has what we call live variables. Similar to reactive programming, it allows you to program a little more declaratively. So here we have a variable x, but we have a live variable y, which we bind to sort of the expression x plus 1. And what happens here is anytime x changes, we reevaluate this expression and store it into y. So y starts off as 42 plus 1, but then as we change x to 666, y reevaluates x plus 1 and stores 667 into y. Yep.
If the body of y had been, for instance, to add x to a random number, then would that random number, if the body of y had been to add x to a random number, so that random number effect has to occur at some point.
Yeah.
Does that occur every time y is accessed or every time x changes?
I think it depends on how you model your random number generator. So in verse, you would probably model calling a random number generator as like it has some value that it mutates on every new call to that random number generator. So in verse's effect system, you would say that random number function both reads and writes. And actually, the right-hand side of a live variable expression can't have a writes inside of it. It can only have a reads expression.
Okay, so you wouldn't be able to do a side effect in that case.
Yeah, exactly.
Great, thank you.
Yeah. So verse has failure. So control flow is done via this construct called failure. So in C++, if you see like x greater than 200, that's an expression, it returns a Boolean. In verse, we say that expression can succeed or fail. So if x is greater than 200, it succeeds, and if it's less than or equal to 200, it fails. And you embed failure within what we call a failure context. So here, the if statement takes an expression for its condition. That condition may succeed or it may fail. If it succeeds, you run the then, and if it fails, you run the else. So here, we're testing if 42 is greater than 200, which it isn't, so we print, we run the code at the else, printing less than or equal to 200. And unification also might succeed or fail. So similarly to the previous example, we're trying to unify x with the value 200, that fails. You can abstract over failure. So here you see f is declared with the decides effect, saying f may succeed or it may fail. So this is exactly the same as the previous example, except the function f is doing the thing where it's testing if I is greater than 200. Failure contexts show up in a lot of places in verse, but one of the most interesting places is in the for loop. So for loop, what we call the domain, so like the condition of the for loop, is a failure context. So here, the range, which is the body of the for loop, only produces values for items in the range that succeed. So what we end up doing, like the previous for loop, is we iterate over every value of x, but we only run the body for the elements e, where e is greater than 6. So we end up producing just the slice of the array here, where the element is greater than 6. So for loops in verse are sort of both map and filter built into the same construct. Next, we have sort of the intersection of failure contexts and transactions. So again, the unit of work in verse is a transaction. So when verse is running, it's always running in a top level transaction. And if you remember the coroutine slide, we have these functions that are suspends, and a transaction in verse is running between two suspends points. But you can also have a nested transaction in verse, and every failure context creates a nested transaction. So what's happening here is we have this var x, which starts off as 42, and in the failure context, we first set x to 666, but then we test for y less than 0. That fails. And what that ends up doing is failure in a failure context is also aborting the transaction of that failure context. Does this example make sense to people? Yeah, exactly. Yeah, so this is creating a nested transaction. The effect in this nested transaction is just one thing. It's writing the value 666 to the pointer x, which is a pointer to an int. And that store to memory has to be undone if the transaction's aborted.
So if I'm not putting this y smaller than 0 in this if branch, it's just like putting in a no more like sequential statements. Does that like negate the entire?
So a top level transaction is running in a context that's not decides. So a decides context has to be embedded within a failure context, but we are always running in a transaction. So the way to abort the top level transaction is actually via a runtime error. So you can still abort it, but the program y less than 0 at the top level wouldn't type check.
But if you put it in a function, then that is annotated decides if it fails the whole function is aborted.
Yeah, like this. So like here, if you also had effects inside of f, if I were less than or equal to 200, those effects would be undone. And that nested transaction, so this is the version of the nested transaction that fails, therefore aborting the transaction. But you can also have a version of that transaction that succeeds. And when the transaction succeeds, that transaction is committed. So the inner transaction that sets x to be 666 commits. And then when you print after that transaction, x is still 666. And I think kind of getting at what Jan was talking about, like that one write to x isn't the only effect that's possible, right? Here you can have any arbitrary effect happen, and if y is greater than or equal to 0, it should be as if that effect never happened. Does that make sense? Yeah.
Does it propagate to the function that is not pure? Like, say, does it propagate to the function that is not pure, saying that I'm printing something, right? Or like sending a packet?
Right.
Or are you going to commit the effect after?
Yeah, so like some effect here might be like send an RPC from one process to another. Yeah, so that's actually like really interesting implementation detail. So we usually have code, like the code we've written along those lines have often been like, send this RPC packet once the transaction commits. And in that case, it's the top level transaction, because you can have, this transaction can be nested somewhere way deeper in the transaction stack. What you care about is if my root transaction commits, then send the RPC request, or then store the file to disk. I think there's.
So you keep saying on one hand that, oh, and if the transaction aborts, then we undo it. And you also say if it succeeds, then we commit it. But like, how should I put it? Like only one of these makes sense, right? Because either you say that things don't really happen until they get committed, or things happen instantly, but they might be undone. So which one is the model here?
I guess I don't.
Yes, but is there something happen, like is
right, so when you're in this transaction, so I don't know if I have a pointer. If you're running code here, that sees x as the value 666. So while you're running in the transaction, the heap is as you've been mutating it in the middle of that transaction. So committing it is not a lot of work, right? Like you've already performed the mutations you wanted to. So code within the transaction sees as if the transaction will commit. It's just if failure is encountered, it's as if no effect in that transaction happened at all.
So maybe what I want to ask is rolling back expansive or is committing expansive?
Rolling back.
Okay.
The way we've implemented it.
Okay.
Yeah.
That could have been implemented the other way, right? I mean, it's just an implementation choice at that point, right?
Yeah. It is an implementation choice in terms of the performance cost, but the semantics are not an implementation choice. The semantics inverse are well understood, yeah.
Suppose I had two effects back to back, one of which was sending a message and one of which was receiving it.
Yeah.
And after both of those occur, then I have a choice that might possibly fail.
Yeah.
It seems like it would be very hard. So for instance, if the message I receive is a function of the message I send, and there must be some real world other server that has to have actually gotten that message, how can you reverse that?
So the only way to see the passage of time inverse is via suspends context. So to see the passage of time, you have to have executed a suspends function and then resumed from it. So if we created APIs for like send network packet, receive network packet, those would both likely be suspends calls. So they would be one like you can't, we don't allow you to write that suspends call in the middle of a transaction in a middle of a failure context. They can still be in the middle of a transaction because verse is always running transactionally, but the only way to abort that transaction is via a runtime error.
You can't act on the outside world and see the result within the same transaction.
Yeah, exactly.
It is a domain-specific language for gaming, right?
Yeah, but like launch the nukes would be a suspends function in verse.
And so mutation in this case is a special case where it's
Well,
something that
mutation
is
isn't seeing the passage of time, right? So the way to think about verse is that like a transaction, here's how I think about it. Transaction executes instantaneously, and sequential transactions are where the observation of time can happen.
but I can observe within the same transaction a mutation that has happened in this transaction.
Absolutely, yeah.
So doesn't that kind of violate that reasoning where it
So
seems like I would have to wait
So
until.
sending a packet, what you can view that as is code that runs telling you to commit the transaction you're in, then you send the packet in its own isolated transaction, then you run the code after sending the packet in the subsequent transaction after that.
Okay,
That's how I reason about it.
okay.
This is good stuff. So
I'm not sure what you call the thing inside the if condition, but
yeah,
let's call
a
that.
failure context.
Okay, so in a failure context, you can be kind of monadic over function calls that only have effects that can be rolled back, but you can't be monadic over functions that, or anything that has effects that you can't roll back. Is that what's basically going on?
Yeah, sure. That's one way to think about it. Yeah, like you can't put launch the nukes in a failure context.
Yep, okay.
All right, talked about that. So next is leniency inverse. So this is what I was talking about earlier where programs can run out of order. So here we have a unification variable x, it's of type int. It doesn't yet have a value. We print x and then we unify x with 42. This does what you would expect it to do. It would run the same way as if you moved that unification above the print. Similar to our previous example, you can not just print unbound unification variable, you can have expressions that run across unbound unification variables. So here, y is unified to 2 times x before x has a value, and we print y before y has a value. And this prints what you would expect it to print. And you can abstract over leniency. So here we have a unification variable, we pass it into f, we multiply it by 2 before x, or I, when viewed in the f context, has a value. Does this make sense? This is one of the more tricky things in verse, yeah.
What does the closed mean?
Yeah, let's ignore the closed for now.
Okay.
Talk to me later, yeah. It'll show up in a couple more slides. Let's ignore it for now. I have a slide about that in 1 second. The programs, effects run in program order. So here, also you can have a function that takes in a unification variable and unifies it within the function. So here, kind of ignore both calling f with square brackets and the closed. We can talk about that elsewhere. It's sort of not the interesting thing here. And these values in verse are really unification variables. So here we have 3 unification variables, x, y, and z. We unify x with y, y with z. So after that point, x, y, and z are all equivalent to each other. And just by unifying z, it's as if, because there's an equivalency, all variables gain values. Does this also make sense to people? Cool. Here, similar to this example, of course, you can abstract over this. So similar to what you're asking, what happens with leniency and effects? So here we have a program. The effects in this program are writing to X on line 3 and line 4, reading from X on line 5, writing to X on line 6, reading from X on line 7. These effects have to happen in program order. That's the semantics of verse. But notice that the then and the else of the if statement both are effectful. And we don't know if we should take the then or the else until y has a value. So here, we run this entire program before unifying y with the value 201. And only after we unify y can we then determine that we should be running the then statement. So what happens in verse is it's as if that y equals 201 were hoisted to line 2. That's the way to think about how this program executes. So once you unify y with 201, that allows the failure context to determine it succeeds. That runs the then on line 3. That running that then allows the read on line 5 to execute. Running that read allows the write on line 6 to execute. Running the write on line 6 allows the read on line 7 to execute.
It'd be a correct way of modeling in my head that when you get, like you start from the top, and when you get to branching on y greater than 200, it's blocked on not having a value yet for y. So you like queue it somewhere, the continuation, which is both branches at this point, because you don't know which one to get. And then you keep going, and it gets unblocked when you know that the unification of y could potentially give it a value, and now it is a value, so then it unblocks this. Is that a good model of thinking?
Yeah, and that's actually a little bit how we implement it. So I'm going to talk about how we implement leniency in the new VM in the next section. You have a few people.
Oh, how it runs when y is dependent on x?
So depending on how you wrote that program, that would be stuck. The verifier would say you can't, there's nothing it can do to unblock this program, so it would be rejected by the checker.
Possibly a very obvious one, but I assume if you didn't set x in one of those branches, it would still have to wait. Like the possibility that x might get set means that you have to wait on those.
Yeah, because you don't know if you're running the then or the else until y gains a value.
When do the reads of x happen on those prints? Does it happen before you call the function?
Yeah.
Okay.
One more time.
Sorry, I know this is probably going rather long.
That's okay. Well, I'll skip around a little bit later to make sure we finish.
So suppose I have so you mentioned that there's a verifier that makes sure that a variable is assigned. Is that it seems like that verifier need necessarily be conservative, right? In the same way that I might have, if this Turing machine halts, then assign a value and then print that value, right? That only, the verifier would then need to solve the halting problem in order to correct that problem accuracy. So is it conservative? Is it overly liberal in that it will sometimes allow those kind of stuck states to occur?
The verifier will never, so this verifier isn't finished yet, but the goal of the verifier is to never allow a program that's stuck to check.
Okay, that makes sense.
All right, let's talk about the new VM. So I told you at the beginning, you can publish verse programs today. So we have an existing VM. The existing VM is built on top of Blueprint VM, which is a VM designed by Epic for the Blueprint scripting language. It's a visual scripting language. It's not designed for verse. The part of the language implemented in what we call the old VM is ship verse, which is really reduced subset of verse. Doesn't have unification variables, doesn't have leniency, doesn't have lambdas, doesn't have live variables, doesn't have a lot of things that we want to build into the language. So there's just this huge impedance mismatch as we implement things in the old VM. It makes it really difficult to implement new language features. This is not a VM designed for verse. It's also really inefficient. One example of that inefficiency is like any object in the system is like 400-ish bytes or something like that. So our new VM, designed for what we call maxverse. Maxverse is the fully realized version of the language that Tim wants. It has leniency built into the semantics of how we execute bytecode. Smallest object size is 16 bytes. We still support compatibility with UObjects. That's how folks writing sort of FFI APIs to verse, they use UObjects. We can still support them. We have what we call Franken GC. So Unreal Engine has an incremental stop the world garbage collector for UObject space. We, for our vcell space, have concurrent mark and sweep, so we can mark concurrently and sweep concurrently while the mutator is running, but the UObject space can only mark with the world stopped. And one of the guiding principles for the VM is static in the front, so verse is strongly typed, but verse is also highly dynamic. So the VM is itself dynamic. For example, there's only one add bytecode in the VM. It both is responsible for adding ints, adding floats, adding two arrays together, stuff like that. The bytecode format is a linear instruction stream, register-based, untyped. The unit of value is what we call v-value. These are 64-bit NAND box values. Control flow is done primarily through failure. And unification and leniency are like built into the interpreter and bytecode semantics from the ground up. We can skip this. V-values are 64-bit NAND box values. This is what a bytecode instruction looks like. Here you have the add instruction. Takes two inputs. The left side is R1. R1 is just a pointer into the frame. R2, the right-hand side is also a pointer into the frame. We unify that result with R3. We'll get into unification in a second. That's what a bytecode instruction looks like. Here's a really simple example of one of these programs running. So here we have the bytecode for F. F takes two parameters, multiplies them, returns them. So we see that when we're running F, if we called it with 42 and 2, we can see R1 and R2. Those are the two arguments to our function. I'll have the value 42 and 2. We see we run this R3 arrow reset instruction. What this is doing is creating a fresh unification variable. We'll get into that a little bit more in a second. We then multiply R1 with R2, unify it with R3, and then return that from the function. This is pretty basic bytecode interpreter, register-based bytecode interpreter stuff. All right. So now let's look at how we do leniency. So here we have this function f. Similar to our previous example, takes one parameter as input, but you'll see that we multiply x and y together before we have a value for y. So here, R2 is y, and R3 is z. So we create unification variables for R2 and R3. And then the interesting bit happens here. So we don't actually have a bound value for R2 or R3. But what we want to do is run the instruction mul R1, R2. Sorry, we don't have a bound value for R2. R1 is a bound value. It's the parameter to this function. But we don't have a value for R2. So we can't actually run this multiplication yet. So I'm going to talk about how we do that. So the main idea, I think similar to what you were getting with your mental model, is how do we execute these lenient semantics? So the VM is designed really with this idea that computation can be captured into what we sort of call like a suspension closure, which closes over all of the inputs necessary to perform the computation. So in the case of mul, it will capture dynamically when it encounters leniency, both of its inputs and its output, into a closure. And then when its inputs are resolved values, it will run that closure and unify with its output. So unification variables in the VM have 3 states. All unification variables are created as what we call a root unification variable. So when you run the reset operation, we're creating a root unification variable. And then there are 2 primary transitions that happen. So you can transition from root to value. So this happens when you, let's say, unify x with the value 42. But something really interesting happens there. So when you're a root, you have a list of suspensions that have to run once you gain a concrete value. So when you transition from root to value, you take this list of closures and then you execute them. You can also transition from root to pointing to a parent unification variable. That happens when you unify 2 unbound unification variables. And what happens there is you pick one to point at the other, but you join their suspension list together. And these unification semantics are built into the bytecode. So what we have, when you see equals in our bytecode textual format, what that means really is you're unifying with the result of the operation. So it's not just a def, it's both a use and a def. And then we also have what we call a clobber def. That's that arrow, and reset is actually the only operation today in our bytecode that has these semantics. And that writes directly into the frame. And reset is the only operation that does this, and all it's doing is creating you a fresh unification variable. So if we go back to our example, look at it a little bit more detail, we see that we have 2 placeholders. We have a placeholder for R3, which is just a unification variable for R3, and we also have one for R2. Let's call those P2 and P3. They're both starting off as these root unification variables, and they both have an empty suspension list. So when we go to run this mul, we see that R2 doesn't have a value. And what we do is we create this closure called a mul suspension that captures the left-hand side, that's the value 666. It captures the right-hand side, which is P2, the placeholder or unification variable for R2. And it also captures P3, the output of this operation. And then it also enqueues itself on P2's suspension list. So when P2 is unified with a concrete value, we run this mul suspension. And then the next instruction will unify P2 with that concrete value. So it unifies P2 with 42, so you can sort of see that designated.
But shouldn't S also be blocking on P3? Because, you know, if I know that X times Y is 84, and X is a parameter and it's 2, then Y can be solved by unification as well. You can go either way.
Yeah, sure.
So in this,
yeah.
And does that work?
So that like sort of prologue style evaluation isn't built into verse directly. Like you have to write code sort of manually to get the like backwards aspect of that.
Oh, so there is directionality here.
A little bit, yeah. But it is true that you can also have another line of code which says Z equals, or Z unifies with 84, and that must hold, but it won't solve for Y.
Yeah, that's what I meant. So there is directionality.
So it won't solve.
Yeah,
it won't
okay,
solve for Y.
okay.
Yeah.
Suppose that you had 2 suspensions which were mutually exclusive. So say one of them was a suspension that, oh, this is the product of two variables which are both positive numbers. And then another suspension which says that same variable is the product of a positive and a negative number, such that one of those two suspensions must be untrue. Is the verse VM?
Yeah, you can fail. So there's no guarantee when you either run in order or via suspension that the unification succeeds.
Okay.
All unification might fail. Yeah, exactly. Yeah, you have to evaluate everything. Like both of those suspensions will eventually evaluate, and one will fail based on your construction.
Okay, thanks.
Do you perform occurs check on it?
A what check?
Occurs. Like
What?
can Z use itself in what it is supposed to unify?
I think that will be stuck by the verifier.
Okay, so you can't, because sometimes you can generate structures with this.
Oh, like Z equals Z times 2?
Possibly, or Z equals Z times 1.
Sure.
Or you generate
that's-
a
the VM
lazy
will-
structure which...
yeah, the VM will execute that faithfully.
Okay. And also, another question, does L value need to be a variable, or can it be a pattern as well, or like an expression too? Can I write x plus 1 equals 1 plus x?
I think so. Yeah, why not? Yeah, definitely. Okay. Yeah, all values are unification variables and at the VM level, but I think also you can definitely write x plus 1 equals 1 plus x.
I'd like to clarify what I think the previous question was trying to ask. So I assume this is all shallow. So if I have some tree-like structure, I can have a function that is only blocked on solving the top level of that. Like let's say it's literally a binary tree, then I can have something that's stuck on whether the top is a leaf or a branch, sure, without knowing it. And then in this case, the occurs check question makes a ton of sense, because then can you have something like T equals a binary branch of T and T?
I'm not sure I'm following T and T.
Please stop me. Okay, so you can't even have like an infinite list, which is like...
But the interesting bit there is the VM isn't opinionated about that aspect. I think that's actually like a detail of the checker that's like, yeah. All right, so we were here. We're unifying a value with R2. That unlocks the multiply from running, which then unifies the value with R3 in the unification variable P3. We see that here. P3 now gains this 27972 value, and we can return it from the function. I think I'm going to skip this because I'm running out of time shortly, but does that make sense? If people want to see like a more interesting leniency example, feel free to come talk to me. There's interesting ways that like are beyond just one instruction. I will also skip how we optimize this. I guess I'll give you a really quick high-level overview. We don't actually allocate a unification variable for every value in the program. That would be super wasteful. So one key optimization we do is if you create a unification variable and you never unify it with another unbound unification variable, and if you unify it with a concrete value, essentially the isRoot thing where you don't have a child pointing at you, we don't heap allocate you, and when you go to unify, you just store that value directly in memory. Okay. So a turn from leniency to transactional memory. Anyone have other questions on leniency before we go to transactional memory? All right, cool. So this is our transactional memory example from earlier. Nested failure context, setting x to 666, that fails, reverts the store to x, print x, it's 42. So what happens when that set x equals 666 is actually some function written in C++ code? Right? We still want that function to undo all its effects. And this really was the motivation for creating AutoRTFM. So today in the API exposed to verse programmers, we have over 300 APIs backed by C++ code and Blueprint code. Blueprint is its own bytecode format that runs via a C++ interpreter, so we can also run that Blueprint code transactionally. And UE has more than 16 million lines of C and C++ code. I think this is CLOC of unrealengine.com/engine, so it doesn't even include all the Fortnite code. We wanted an approach to transactionalize all this C++ code that was largely automatic. Our old approach to this were extremely manual. We had two functions, basically, on commit and on abort, and then every function that was transactional and written in C++ was written using these two primitives. And I think basically every single version of this function I saw got it wrong somehow. So no one got it right writing code this way. So AutoRTFM stands for automatic rollback of transactions on failure memory. Of course it does. So what is AutoRTFM? So it's a single-threaded implementation of software transactional memory for C and C++. It's built on top of LLVM and Clang, and we have a tiny runtime to go along with it. So the main architecture of AutoRTFM is we run at the end of the LLVM optimization pipeline. We take the entire input program and we clone it to create a transactional variant of every single function. The main thing that transactional variant does is record all stores to memory. So what we're trying to do is intercept before a store happens to memory so we can record the old value of that memory location, so when a transaction is aborted, we can undo it. This is what we call the write log. We also insert traps for unsupported instructions. For example, this is the 16 million lines of C++ code, like that code will like grab a lock, for example, right? So what do you do in that case when you're trying to make it transactional? Today, we don't allow the code running under the transactional memory runtime to do that. That'll just be a crash, and the code has to be rewritten to accommodate it. So terminology, we call the uninstrumented C++ code open. We call the instrumented C++ code closed. And we have these primitives. We have transact, it takes a lambda, runs that lambda in a new nested transaction in the closed, so in instrumented code. You have the abort primitive. This aborts the transaction you're in. You have open that takes a lambda and runs that lambda uninstrumented. So it's sort of same old C++ you know. You have close, which also takes a lambda, runs the version of that lambda instrumented. And then you have those same two on commit and on abort callbacks. And on commit runs the input lambda when the root transaction commit, and on abort will run the lambda it's passed when the transaction or any parent transaction it's in it aborts. So I think someone was asking me about like RPCs earlier, like the way we implement RPC under this scheme is like on commit send RPC. So we're gonna, similar to learning verse by example, we'll learn AutoRTFM by example. So here, pretty simple code. We have a int x outside of a transaction mutates x, and of course we print the mutated value. But that transaction might also abort. And when it aborts, we undo the store to x, and we print the original value prior to the transaction, which was 42. This is what the code would look like to you if you were programming against the AutoRTFM API. So like you as the C++ programmer working at Epic, this is the code you see. Does this make sense?
Your transaction usually transparent.
Yeah.
You wouldn't write this.
You would write the transact part for sure, and you would write the abort part.
And the open version of this, does that just set x to 666, or does
Yeah,
it?
the open version of this sets x to 666, but if you ran abort, that would, if you're not in a transaction, that would crash because it would be like, why are you calling abort from not within a transaction?
So the open version of this crashes after setting x to 666?
Yeah.
Okay.
So you can have nested transactions. So here you have a top-level transaction. That top-level transaction sets x to 666. Then the nested transaction increments x. Both transactions commit. You get the expected value. But of course, your inner transaction might abort, in which case the top-level transaction, the store to 666 succeeds. You then run the inner transaction, increment x to 667, abort that transaction, revert the value back to 666, and then that's what's printed after the transaction. The code in the open isn't run transactionally. So here you have a top-level transaction. It stores x to 666. Then in the open, we run code that increments y by 1, and then we abort the transaction. So the store to x will be reverted by the transactional memory runtime, but the store to y wasn't instrumented by the transactional memory runtime. And therefore, y is incremented from 0 to 1, not transactionally. This, in practice, is like useful if you have logging and stuff like that, to run that code in the open, not transactionally. We have these on-commit, on-abort APIs. So here we have an API where we increment x by 1 on commit, and then we decrement x by 1 on abort. So here we have a transaction that commits, so we end up setting x to 666, then on commit, incrementing x by 1, so we end up with 667 at the end. But of course, that same transaction, we might abort it, and in that case, we first undo the stores to memory, and then we run the on-abort handlers. So we undo the store, reverting x back to 42, then we run the on-abort handler, decrementing x by 1, we end up with 41. So here's sort of what happens in the compiler when we go to implement that code. So the code on the left is like what you as an Epic developer sees when you're writing C++ code. The code on the right is what our compiler instruments and inserts into that closed variant of the function. You see this record write call before the store to x. And so record write takes 2 parameters. One is a pointer, one is the number of bytes that will be stored to at that pointer location. So here int is 4 bytes. And what we'll do is for the first store to x in the transaction, we'll record that in what we call our write log. And then if a transaction aborts, we undo the write log. I guess, interestingly here, y is a local variable to the transaction. It doesn't actually need to end up in the transaction log. I'm gonna skip over that mostly. So how does this work at a deeper level? So for transact, we still have the record writes here, but when transact runs, we create a landing pad for the code to land back at when an abort happens. So we actually use set jump, long jump for that. So transact will set jump, we'll create, allocate a transaction data structure. The inside of this lambda is similar to what we saw before. And what abort is turned into is essentially undo the write log, run the on abort handlers, then deallocate the transaction, and then jump back to where that transaction started. And if you reach that else branch, it means that the transaction was aborted. Any questions on that?
So I'm wondering what happens. I guess you can also have functions calling more functions in your lambdas, right?
Yeah, totally.
And those, if you have them instrumented with your client, then those would all be marked, I guess. But do you know if you're calling functions that are not compiled with your runtime?
Yeah,
like
so
if someone just imports some other library and then links it against it, and then stuff just goes horribly wrong.
Yeah, we have like decoding libraries that are are included in Unreal Engine, not at source, but like on an
Right.
executable level. So far, we've been able to run all of those just in the open, and it's fine. Stuff like that makes that easy. But if we had a scenario where we had to recompile it, I think we would.
Okay, so you don't have any form of tagging on those functions to have like
No.
some meta information. Okay,
No,
thank you.
I was expecting just the long jump to be in the IFC and all the ceremony to be on the side, like in the else branch.
Yeah. I think you can. So I'd have to remind myself why it's this way, but I think it has to often do with you want your stack frame to be there if you're undoing any writes to it. This is also just like what the code does today, so I transcribed it literally to this. There might be some subtle reasons I'm not remembering why. Because when I went to read the code to make this slide, I also in my head thought it would exist on the else branch, but it doesn't. So let's look at an example real quick. So here we have two variables. They're written to by the transaction. So here we have a pointer in memory, we have a write log, and we have the actual value in memory. So when we go to run this function, before we store x to 666, this was the first time this transaction is storing x, so we record the old value in the write log. Then we actually store x into its address in memory. Then we record write x again, but x was already in the write log, so we skip writing x, the old value of x to the write log. If we did that, we would be undoing x to the wrong value when the transaction aborts. Then we increment x by 1. Same thing when we record write on y, we store the old byte to our write log. Then we actually do the store to memory. And then when we go to abort the transaction, what we do is we run through our write log and revert the values that were in the write log to memory. So in this case, we return the values to 42 and A. I will skip this example, but if you're interested in a transactional malloc and free, ask me afterwards. So how does RTFM and the new VM interact together? So the new VM is run completely uninstrumented. It handles transactional memory for verse, the verse heap not written in C++ code on its own. It has its own transactional data structures. We want the new VM to be really fast, and this approach has a cost on performance. But the two software stacks are tied very closely together. So when you have a failure context in the new VM, that actually starts an RTFM transaction. And then when the VM calls into native APIs written in C++, it transitions from open to closed along that boundary. So let me quickly give you some results. So auto RTFM, if you go onto Fortnite today and you play a UEFN island, that's running on a server with auto RTFM compiled executable, and it's on at runtime. So that project shipped as of a couple months ago. I think we started it maybe 2.5 or 3 years ago. And then the new VM we started almost exactly 2 years ago and is gonna begin rolling out in November, and I think we'll probably be done, if I had to guess, probably like March of next year. Auto RTFM is not free, right? So the cost we've seen, this number is coming from running a set of benchmarks on Blueprint VM. So this might in some ways be a pretty aggressive example. We're running an interpreter through auto RTFM. What we've observed is about like a 3.5x slowdown in that case. And what results have we seen for the new VM? So the new VM is already like 5.25x faster. This was taken 2 months ago, so I don't know where we are today. But this is sort of ballpark how much faster we are. And we've spent very little time optimizing the new VM already. We've obviously thought deeply about its architecture and making it efficient, but like this is just the beginning, right? We just have an interpreter. We don't have a baseline JIT. We don't have an optimizing JIT. We do no speculative optimization. And looking at So this is result on what we call vbench. Vbench is just like a benchmarking suite we created. It's not as extensive as we want it to be yet, but it's a kind of a good BS check of how fast we're performing. If you break that down into individual benchmarks, this is how we're doing on those. We're faster across the board. And I think we can get a lot faster. For context, we're, I think, probably like 10x slower than a JavaScript interpreter for a similar program. So even though we're much faster than what we used to be, we're still pretty slow. I'll skip that and leave it some time for any more questions.
I guess one of the things mentioned in the beginning is that you're looking for soft real-time guarantees. I guess how does there's some tricky stuff going on with the VM that feels like it could potentially be a counter to that. So I'm wondering how well are you finding it fits the soft real-time guarantees, and what sort of engineering decisions are potentially related to that?
I think the main decision we made to meet that guarantee was just having concurrent GC. I think largely we're relying on developers writing their games to be fun, and to be fun, you don't want your game hitching. So we're largely relying on them putting in the work to meet like the fun criteria for a game. We're not doing much else besides that. Obviously, lots of choices in Unreal Engine are within this constraint, so we're just living with those choices.
So in the previous example, you mentioned that you can put open in a transaction. So do you see people using that in a creative way to, like, say, this is a new programming model, right? Yeah. So if you put some open, then people can bring themselves back to the comfort.
So the interesting thing, this project has taken, what, 2.5 years. The hardest part is actually that one bullet point on the first slide, which was all of the illegal instructions are code we've had to go and change and make work within the system, but still we find ourselves where like 99% of the system is transactionalized automatically. When we first began our conversion, so like that 2 years, we often were moving code into the open, and we found that actually, with our approach, leads to lots of bugs, usually memory corruption bugs. Let me give you an easy example. If you have an array and you mutate that array both in the open and the close, you're gonna have memory corruption. So our current approach is to put as few things in the open as possible. But if you look at this example, which I didn't get to, if you look at malloc, what I forgot on this slide is that this malloc impulse should be called in the open, but actually there are parts that are really critical that do run in the open. So the way malloc is implemented is we malloc in the open, and then if you abort that transaction, we free it for you.
Sounds good, thanks.
Do you have idea what the overhead of your STM is on the C++ code?
Yeah, like 3 to 3.5x.
Are there optimizations in STMs that you think that you'd be able to apply here? Like, for example, like you don't have to write to the write log for new objects and things like that?
Yeah, so we do have some of those optimizations. So if you're newly allocated memory, we have like I think it's a red-black tree where we track that, and we skip, so testing for that is more performant than performing the write to the write log. So we do that. For the VM's transaction log, I've played with an idea for epochs, so tagging every allocation with an epoch, and if you write to and epochs are monotonically increasing, and every new transaction bumps the epoch count, and every allocation can grab its epoch from the epoch count, and then you can elide writes to the transaction log if you write in an epoch that's less than or equal to your allocated epoch. That was inconclusive if it made anything faster. I think that might end up being profitable, but there are probably other ideas we haven't explored also.
How does the distributed STM work?
Right, so the whole metaverse programming vision that Tim has, we're working on something called distributed software transactional memory. It's not, the goal of that is not yet to be persistent, but it is to write code that largely looks single-threaded, but is distributed across multiple machines. And AutoRTFM is a foundational technology for that. So what you have in our model is objects that can be owned by servers. And if your C++ code tries to access an object not owned by your server, you actually abort the transaction, request that object be migrated to your server, and run the transaction again. So like this technology we've built has actually been really useful in other projects we're working on.
So I have a question about the application of this logical part. Looks very interesting from the programming language design, but I wonder how it is useful for game development. Like why, why do you need all that unification magic for scripting games?
Yeah.
Ideally, if you have some example, that would be awesome.
I don't know if I have a great example for that. I think there are aspects of the logic stuff that's useful. I mean, to me, I find more of the functional subset more useful than the logic subset, especially because there isn't, like in Prolog where you have the search space semantics built into the language, that's not built into verse, which to me I view a little bit more interestingly. But I think, I don't know, I don't have a good answer for you on why do game programmers need logic programming.
Because Tim said so.
Well, that's why we're implementing it, but that's not I'm not going to convince you with that. No, I don't think so, yeah.
So I have kind of a related question. For the shipverse, so you already have a few of the esoteric features, I would say. Did you like study how developers use them? Do you have like...
Yeah.
Because they have access to the code, so do they actually use this kind of... this kind of features?
So shipverse doesn't have leniency, doesn't really have unification variables.
Okay.
In an interesting way, does have software transactional memory.
Okay.
Does have coroutines. The most interesting part of the language I've seen used widely is coroutines. Like I talk pretty regularly with verse developers, and it's really interesting to speak with them because they kind of don't care about the language. What they care about is making really fun games. Coroutines are the most like extensively used feature of the language. Like I didn't talk about it at all, but there's a lot of constructs we have for writing cooperative multitasking code using coroutines really easy. And that's like the thing I see developers using the best. I don't see them using software transactional memory in interesting ways. But yeah, coroutines are probably the one they use most interestingly.
All right, well, thanks a lot, Sam. And let's thank the speaker.
Thank you.
So the next speaker is Takashi, who's going to talk about the new JIT compiler for Ruby.
Testing.
Do you want me to signal like 5 minutes? Sorry? Do you want me to signal you like 5 minutes before the end of the talk?
Yeah, that'd be great, I guess. Yeah. If you're gonna wave or something, yeah.
It's pointing this way on purpose. Someone told me apparently it makes it harder for it to make loud booms when you go.
Oh, yeah, yeah. So, like, I should still talk to this direction? Like,
Or just past it, just slightly next to it.
Okay.
Then the air goes here and the sand goes here.
all right, interesting. Thank you.
Hi, everyone. Today I'm going to talk about ZJIT, which is a new JIT compiler we are building for the Ruby programming language. I'm Takashi Kokubun. I'm on the Ruby JIT team, which is part of the Ruby infra team at Shopify. We have like 40-ish people working on Ruby-related OSS, and Ruby infra team is like part of it. And then we have like 7-ish people working on JIT, and I'm one of them. I had also been working on like Ruby JIT for like 8 years, like even before Shopify started working on Ruby JIT. So like, and then I've kind of either authored or maintained 5 different Ruby JITs. So yeah, I'm kind of addicted to optimizing Ruby. So I'm gonna provide a background, assuming some of you have not written Ruby, but how many of you have written Ruby before? Any amount of Ruby? Thank you. Many of them you have written Ruby. So it's an object-oriented language, not just object-oriented, but also pure object-oriented language, which means anything in the language is object. Like, for example, integers are also an object and could be modified, and like, there's no primitive types like Java, for example. And that's also dynamically typed. Like, there's no type signature in the function declarations, or variables don't have also like type of signature. So if you have a variable or argument, that could be any type, and that allows the dispatch of anything. So let's say you have a variable and you do a method call on it. The receiver could be any number of different types. So you need to sometimes do the dynamic dispatch even if you specialize that in the JIT code. There's also a lot of meta-programming features, such as notably eval or any programmatic access to almost every part of the language. So to give you an example, this is a 1+2, but as I said, everything is an object, so integer is also an object, and this is object-oriented programming language, so like this is a class definition for the every integer, and it's also open class. You can redefine any method on the class at any time. So integer plus could be different to like something else, like returning thousands here. Another example here is this is also dynamically typed. So as I said before, the variables or arguments can be any different type at any time. So if you give a integer 2 to this like integer plus looking code that returns 3, but you could also return random class you define, and that same the method needs to handle different classes there. I'll give you some other features that make it hard to optimize. So here we define the local variable n equal 1 and then print it. But there's, as I said, there's an eval. So like, and then eval is also not a keyword. So any random method call with a string argument could modify the local variable. And there's also programmatic access to local variables or any other like type of variables, like for example, instance variables also have a programmatic access. So this binding is a method call as well. Like really allows you to call a method without parents. So binding is a method, and then it evacuates, escapes the local variables to the heap. So it returns a binding object that has every local variable, and it allows you to call this local variable set method that modifies the local variable n in the heap object. And once you escape the binding, then that frame will refer to the local variables in that heap object. So the caller method will be able to see the local variable set by the local variable set. And another very bad API for optimization is that you can also get the binding object of caller frames. So whenever you call a random method, that could also call another method that could like escape the binding of caller frame. So whenever you make a method call, you need to be prepared for every local variable in the frame is modified. And there's also a tracing feature that allows you to do that kind of thing. So like in this last example, whenever you go to the next line, that triggers the line event and increments every local variable in the top level frame. So we are dealing with that kind of stuff. And there are 3 major Ruby implementations that are relevant today. So like there's a CRuby, which is the thing I'm going to talk about mainly today. CRuby, as the name suggests, is written in C. It has a stack-based interpreter. The bytecode is stack-based, and the JIT is a retrofit, so it's still not enabled by default. If you just run the Ruby command, it doesn't enable JIT. Another thing is JRuby. So JRuby, the J suggests that it's a JVM-based implementation. The Ruby source code is parsed into the bytecode for the Java virtual machine. And because JVM has a JIT, it can JIT the bytecode. There's also TruffRuby, which is originally implemented in JVM, but also has an AOT that can compile some of the implementation to the native code and starts with the native code and then also runs the Ruby scripts with the JVM. And TruffRuby has the best peak performance out of all these, but we still invest in implementing our own JIT for the CRuby. Which is because all these other implementations have some things that are not suitable for our use case at Shopify. So for example, JRuby is implemented on top of JVM, and as a result, it doesn't support the C extensions today. It used to support, but it stopped supporting them. And we, Shopify, use C-based or native-based libraries such as gRPC. So we use a Ruby library that has a binding to the native library, but on JRuby, you need to rewrite everything in Java or Ruby, so it doesn't suit our use case. And for TruffRuby, it supports the C extensions. They compile C into their bytecode by LLVM. So that works, but it has a very slow warm-up, partly because they have AST-based interpreter. So if you run TruffRuby locally, for example, if you want to install libraries, Ruby libraries, the local command generally runs very slow compared to CRuby. So this is a usability issue if you run the show command locally, or even in production, it uses a lot of memory because of their very advanced optimization. So the peak performance is good, but it's too much memory usage. So we are kind of sticking to CRuby. Though the key difference here is CRuby has a GVL, 2 other implementations don't, but because it has a GVL, we usually are forced to use a multi-process servers. So on the boot of the application, we fork processes, and CRuby may use a lot of memory for each different workers. So even if the single process uses less memory in CRuby might use more memory compared to other implementations. But today at Shopify, we kind of built our own server, Ruby server, HTTP server that is able to periodically fork another living worker to another process. So that triggers a copy on write efficiency. So that original worker shares the memory with other workers. So with that, CRuby has the most efficient memory usage out of these options. So we have a fast warm-up and a small memory footprint, so which is why we're kind of developing a JIT for CRuby. This is a paper we published 2 years ago. We presented it at the MPLR 2023, and that gives a comparison between the 3 different Ruby JITs, the implementations on memory and warm-up. So if you're interested in the actual comparison, you might want to look at the paper. So about CDB. So CDB, going forward, I'm going to mainly talk about CDB by just saying Ruby. So the first Ruby JIT that we merged to the upstream like CDB implementation was called MJIT. So MJIT was uses sort of template JIT. So like we have virtual machine implementation, the bytecode implementation. So each bytecode has a C code that implements the bytecode. So we have kind of print the C code in the virtual machine into like, when you look at the instruction, that prints C code, C code, C code, C code, so like stitched together and then kind of eliminates the dispatch overhead. That also supports compiling the C code with the major like C compilers we wanted to support, mainly like GCC and Clang, but there's also like Windows maintainer who insisted on supporting it, so we also supported the Microsoft Visual C++. That was originally written in Ruby, then we kind of rewrote it in Ruby, but that was mainly C-based implementation. That was good in terms of like some micro benchmarks. For example, if you have a while loop converted from Ruby to the C code using the template JIT, that was able to sort of compile time, calculate the, for example, the increment of the local variable in Ruby, but that didn't go well in terms of, first of all, one issue was the compile overhead. So like, whenever you compile a method, you need to spawn a process of a C compiler, and that takes time compared to other like JITs that we have implemented. So the compile time was a sort of an issue, and also we didn't get to optimize the main use case of Ruby, which is web applications. So Ruby is kind of known for its framework, Ruby on Rails, but MG didn't do well on the Ruby on Rails framework. So we wanted something else that optimized that well. Part of the reason why MG didn't go well is because you need to kind of give some information that C compiler needs for optimizing the logic, but generally the C implementation for the interpreter is kind of dynamic everywhere, so C compiler cannot figure out how to optimize such dynamic dispatches, for example, unless you inline everything and provide every memory, but at compile time, that's usually not available. So the only optimizations we added on top of the template JIT is we sometimes replace the template with something that uses the inline caches and then reads the inline cache and then replace the method dispatch with the optimized method dispatch. But that was not enough to speed up the Rails, so we moved on to try another implementation. So YJIT is the one developed by Shopify at the Ruby 3.1 that uses a so-called lazy basic block provisioning technique that was originally proposed by the PhD paper of the developer at Shopify, who, in her PhD thesis, Maxime. So like, that was in process compared to MJIT. So like, MJIT relies on the C compiler, but the YJIT doesn't. It has its own assembler and converts the bytecode into its own IR, and lower level IR that abstracts the backend. And then it's written in, was originally written in C and then written to Rust. And then we also had another JIT called RJIT that was written in Ruby that has a similar architecture to YJIT, but we added that so that there were some like Ruby developers who were interested in contributing to JIT. So by rewriting, like having the Ruby JIT implementation in Ruby, we kind of allowed them to sort of hack on the JIT compiler itself by opening the class of the JIT compiler, and then, that was sort of a way to let the users of Ruby develop a JIT compiler by themselves. The last thing, the main topic of today is the ZJIT. So because we weren't sort of, the YJIT went well, but we wanted to do things that aren't really easy in YJIT. So we kind of came up with another design that allows you to do cross-instruction optimizations, which is a SSA-based IR, which has a SSA-based IR that was not available in YJIT. So like YJIT was like one pass from like bytecode to the low-level IR, but ZJIT is like bytecode to high-level IR, which does the language-specific optimizations, and then low-level IR that orchestrates the backend. So as I said before, YJIT was a lazy basic versioning-based implementation. Developed by us, Shopify, and not enabled by default in Ruby, but in the Rails is the most popular, the Ruby web application framework, and that's that enables the Ruby, YJIT by default from the Rails version 7.2. So it's kind of like the production RubyJIT out of all RubyJITs in the CRuby so far. And because it's not enabled by default, sometimes when people compare the performance of different languages, they don't enable YJIT by default, so they get like slow performance. But if you, by the way, we kind of had a patch that enables YJIT, but then that improves the performance. It's still not competitive compared to like other pretty optimized dynamic languages such as JavaScript, but it's not as bad as like this original graph. They never update their website, so it's not updated on their website, but if you turn on YJIT, it's slightly better. Though we wanted to do better than this, and we kind of decided that we need some different design for making it faster than this. This is the original lazy basic versioning paper, so if you want to read how that works, you might want to check this out. The reason why we are building the RubyJIT here is like Shopify is the sort of the larger company that uses Ruby by the market cap. So we kind of invest a lot in the Ruby ecosystem. And this is the website that lists only the public companies, but there's also a private company that kind of uses Ruby, which is GitHub. So GitHub also uses YJIT in production, and then they saw 15% to 25% speed up in the production. It might not seem a lot, but for Rails applications, it's kind of a lot. I mean, I'm going to talk about that later, but generally, the community has seen 10% to 20% improvement when they turn on the YJIT flag. So sort of they get those kind of performance improvements for free, basically. So they're kind of de facto standard at this point. So ZJIT, this is what we are building today, this year. So Ruby is an annual release, and we release Ruby on Christmas. So like it's 2 months away from today, and then we are sort of we started development in February. So like it's still very in progress. It's not like ready for evaluation, or even though we need to release that in 2 months, but we want to make it at least comparable to YJIT in the next release, upcoming release. So we started the development in February, and then passed the CB test suite in September with the base of like the IR-based optimization, and also making the optimization compatible with the dynamic features we presented before. So we have a nice infrastructure to start optimizing the language, but this is the current status. So we don't have the benchmark graphs for ZJIT today, but we're going to discuss the designs we want to sort of release this year. So I'm going to talk about the main topic, why we started developing ZJIT. We wanted to develop ZJIT mainly because YJIT wasn't able to do the cross-instruction optimizations. So because YJIT does the lazy basic group versioning for providing, it stops at many places for providing the virtual machine stack and local variables and method definitions. So it sort of splits method into multiple pieces of the blocks, and then each block is compiled separately, so it's generally harder for that design to optimize across different virtual machine instructions. And also because every basic block was compiled lazily and it needed to have the metadata allocated on the heap, we had to sort of be aware of, sort of design what's in the metadata for minimizing the amount of memory we use for YJIT. But because we compile that per method now, we no longer need to sort of care for that this time. So I'm gonna go over how YJIT works. YJIT, so like Ruby in general has a bytecode and then compiled into this kind of bytecode, which is stack-based. So like put objects pushes the object 1 to the stack, and then get constant gets the object constant 2 to the stack, and then the send is a method call instruction that pops the 2 objects from the stack and then dispatches the plus method, and then returns the result 3 to the caller. So YJIT, because of the invalidation reason for the constant, it needs to split the block for the get constant instruction. So it stops at the compilation after compiling the put object. And so because it's only compiling the put object 1, it needs to assign the put object 1 to the register. And then the next block just get the constant and then assign that to the register with the patch point so that you don't need to roll the constant from the heap. And then finally, we have the third block that's just adding the 2 registers and then return that with the patch point of method redefinition so that we don't need to like check the redefinition every time. So because of this architecture, those 3 blocks are compiled differently, and we weren't able to even constant fold 1 plus 2 into 3 because they are sort of compiled separately. It's not a limitation of the lazy basic block versioning itself, but it's more about we wanted to save memory, so we didn't add the, for example, object value like 1 or 2 in the metadata. So as you can see in the context, it only saves the integer type and not the value itself, like 1 or 2. We could have saved that in the context and then do that, but because we sort of wanted to minimize the memory, we didn't prioritize optimizing that. So that's what's happening today with YJIT. So for ZJIT, we have a method, the architecture. So we are going to compile the bytecode, the whole bytecode of the method at once. But to do that, because unlike YJIT, we don't do the profiling as like a lazy compilation. So to profile all the types, we have this ZJIT send instruction. So like whenever a method is called some like multiple times then reaches some threshold, it converts the instruction that needs profiling data. For example, send, the method call instruction is converted to the ZJIT variant that does the profiling. So whenever the interpreter runs the profiling method, that saves the type information that will be used by the compiler later. So that will allow the ZJIT to compile the entire method at once. So with that profiling information, ZJIT is able to compile the whole method at once. And then we have this SSA-based IR. So V1 and V2 are not really compiled into the actual code, but it's there so that we can generate the side exit for the patch point. So like, and when the constant 2 is invalidated, we need to write the object 1 to the stack, so that's there. But for the actual generated code, that's able to constant fold based on the SSA and then just return 3 as the generated code, and with the patch point that's for the constant redefinition or method redefinition. So I'm going to talk about the main challenges in optimizing Ruby and how we are planning on sort of fixing those problems. The first, the kind of like the main bottleneck in Ruby is that C functions dominate execution time. So like we have, so CDB is written in C, but also like this library of CDB is mainly written in C. So the benefit is that you have a very good warm-up performance, but on the contrary, when you JIT everything, then JIT is not able to optimize across the C function call boundary. So like it kind of limits the ZJIT to from optimizing Ruby further from like changing the behavior inside the C function. Another thing is local variables are too dynamic, as I showed before. That kind of has limitations in optimization. We kind of deal with that by invalidation, but it still has things to be done there for optimizing it further. There's also method calls, and because of the dynamic nature of the language, it's pretty slow in the interpreter. And also, even in YJIT, we still execute a lot of instructions, so that's slow. So for the first thing, the C functions dominate execution time. This is the benchmark graph that's before the ZJIT that compares the YJIT, RJIT, and MJIT. These are the three different Ruby JITs that were merged to Ruby before ZJIT. Then you can see so like this is a set of the benchmarks that are like sort of representative of the real world use case of Ruby, which is Ruby is kind of popular for the Ruby web application processing. So these are kind of web related benchmarks. And then in any of these, all these existing Ruby JITs didn't achieve the twice as fast as the interpreter. So there was some comment from Ben that said like JIT should generally give a 10 or 2 times faster than the interpreter, but it wasn't achieving that performance. The reason why is obviously, I mean, in the C2B, even with the YJIT, only 10% of the execution time is spent in the JIT code. If you benchmark applications such as, so we have a benchmark called Lobsters, which is a Hacker News-like website written in Ruby on Rails. And in that benchmark, only 10% of the cycles are spent on the JIT code. So even if you make the JIT code faster, that will obviously not make it overall performance at 10 or 20 times faster. The reason why we spend that few cycles on the JIT code is because we have a lot of polymorphic call sites that will kind of force the JIT to sort of resort to dynamic dispatch. So let's say there's a call site that needs to handle 100 different classes, which actually does exist because the framework has providing base class, and then every user of the, for example, there's an active record class, and then there's an active record base class that's sort of used by so many models that are used by the application. And every single one of the model is going to call into the base implementation that ends up being the megamorphic call site. So that's kind of common in the Ruby programming language. And because we don't want to inline those hundreds of different classes or even more, after trying like 4 or 5 entries of the inline caches, we sort of fall back to the dynamic dispatch. And in that case, we kind of reuse the interpreter information that's written in C. So that's out of the JIT code execution. The same is true for instruction variables. The second one is called IVARs. It stands for instance variables. Instance variable uses object shapes-based optimization, but because that's shared across a lot of different classes, that could also go megamorphic, and that ends up holding the C function for handling that kind of case. And because it's a web application, there's some DB queries spending some time in the benchmark, so 15% is going to be not going to go away, even if we do anything on the Ruby JIT. There's some cycles, of course, spent on the GC, but that's some of them could be optimized by our effort in optimizing the language if we stack allocate objects, but YJIT still hasn't implemented the stack allocation, and we haven't done on the GJIT yet, so that's something to be done. But basically, probably many of them are going to be just escaped anyway in the language, so that's still going to stay there too. And majority, I mean, a large amount of cycles are also spent on the C-based implementations of method. So like there's a string, hash map, and arrays, and also the hash table implementation called ST. So like we do specialize many of the popular method calls on those classes, but we still had to sort of reuse the C-based implementation for implementing edge cases or calling into other like non-so-frequent operations. So as shown here, methods are written in C, and also like when you call into Ruby from the C method, you need to do a lot of setups for setting up the environment for the virtual machine or JIT code. So it has some overhead that needs to be done in the C. And also, as I said before, megamorphic call size also required JIT to spend time in C functions. The approaches we are thinking of are, one of them is, of course, rewrite things in Ruby. So when things are calling into Ruby from C, for example, when a method takes a block that needs to do the overhead of like crossing C to Ruby, so in that case, it's generally, even for the interpreter, faster to rewrite those kind of things in Ruby. So in this example, we just rewrote that in Ruby. But in some cases where the C is actually faster, even for the methods that take block, we just guard with JIT helper that allows you to define the Ruby version of the method and the C version, and sort of maintain two different versions, and enable the Ruby version when the JIT is enabled, which is the current approach. For megamorphic call sites, what we are thinking is we, I think, sometimes need to copy the megamorphic call sites. For example, when there's a loop method that takes a block, the loop method implementation could be copied to the caller of the loop method, and then that will allow the loop method to not make it a megamorphic call site. So like the block is also sort of a method call in the CV implementation. So that will also be megamorphic if you don't copy the array each like a loop method. But if you copy those kind of loop-related methods, then I think the megamorphic call site could be also optimized by the JIT code specialization. For local variables that we showed earlier, YJIT spills every local onto the VM stack, so that will support the heap-based modifications of the local variables, like we showed before. But the C calls and any Ruby method calls also do the spill, and that's kind of how we deal with the dynamic nature of the local variables in YJIT. But in ZJIT, we are kind of changing it to spill that onto the C stack, so that the access will be at least more localized compared to the other native instructions. And then we gave up on making the local variables live in the register in the YJIT on every C function and call, and also a lot of methods are written in C. So spill happens a lot in YJIT, but in ZJIT we pop the right registers across different C function calls. So these are live, and that allows us to sort of fast access to those local variables in ZJIT. So lastly, I'm going to talk about how the method calls are very slow in the YJIT or the interpreter. So this is the native instructions that YJIT generates for the fastest type of very simple method call, but it's still a lot of methods, the instructions. So on every method call, it spends cycles for this amount of instructions. First of all, we need to check the receiver class, and then also Stack Overflow check to raise a Stack Overflow exception. And also, we spill registers on the YJIT, and then the majority of the time is spent on the frame method that allows you to implement the dynamic nature of the language. So these are a lot, but our idea for ZJIT, or what we are planning on in ZJIT, is that first of all, we drop the metadata-related instructions by writing the base pointer to the virtual machine frame, and then lazily reading that off of the virtual machine frame and sort of materializing that lazily. So it's easier to be said than done, but like we need to do a lot of things to sort of make it possible. But yeah, we are working on it to also, make it possible. Because if you dump the instructions for YJIT, oftentimes the method call overhead is sort of dominant in the assembly. So if you optimize the array, the method call overhead like this, I think it's going to be much faster than YJIT, so that's what we are currently working on. So in conclusion, we are building a ZJIT so that we can unblock the cross-instruction optimizations, and we discussed the optimizations we are thinking of for C function calls and like local variables and method calls. That's it. Thank you.
Are there any questions?
My understanding of the lazy basic block versioning is it also was designed for being very low latency. Have you, I guess, do you have numbers for the new JIT to compare? But have you also considered tiering up from YJIT to ZJIT? I don't know if I got the letters correct, but.
Yeah, I think these are good questions. So like for the first one, we've seen the comparison time overhead as well, and then that was sort of comparable. Like it's still not slower than YJIT, but the caveat is that we still have things that are not supported to compile. So like the amount of things compiled in YJIT and ZJIT are not the same, so it's not the right time to still evaluate them. But as of now, it's pretty comparable. So like ZJIT is also low latency, maybe because we still like have a very similar backend in the lowering of the instructions and also do the similar optimization. So essentially, they kind of go through the same kind of optimization. So that's why they're comparable, I think. For the second question, we also somebody's mentioned the idea of tiering, like for example, doing the profiling in the YJIT and then the ZJIT. But the downside is that the memory overhead. So like even with YJIT, people are sort of because the memory is often a bottleneck in the production use of the Ruby. So we want to sort of minimize the Ruby memory usage, and by tiering them, you need to spend some memory in the JIT code, and also the metadata. Actually, the metadata for YJIT compilation is twice as or 3 times larger than the JIT code itself. So we anticipate that if you tier them, the out of memory is going to be spent on just for profiling, which is why we chose the current design.
Peak memory use or steady state?
Steady state. Peak is, fine-ish, but yeah. So even in the peak, because the YJIT does the lazy compilation, you need to keep the metadata forever, basically. So the peak and the compilation generally affects the peak as well, unless you completely change the design of YJIT.
So clearly I need to watch what I say on the Hacker News. Sorry about that. So it's good that you're measuring in context with big benchmarks that do real things. But one thing I'm curious about is how it performs on micro benchmarks. And those have a specific role. Those get rid of the noise of everything that's not your JIT, and that will help you scale up. But maybe you have those numbers?
I do, but I'm sorry. That's so like in the Ruby. Sorry, I wanted to open the browser, but it didn't work. So like we have a benchmark suite called Ruby Bench, and the graphs I showed earlier was one category called headline benchmarks, and then we have 2 other categories. There's other categories that's smaller than this and not the web-related application, and the last one does actually micro. So we have micro benchmarks, and then half of them currently have a very similar performance to the YJIT currently. None of them is currently faster than YJIT, but we've seen things that became faster than YJIT, which is we had some annotations that allow ZJIT to eliminate the method call or inline especially some of the C function calls. So in that case, that was faster. But right now, because we are sort of dealing with the problem of splitting everything on the virtual machine stack yet. So like in the last section, I discussed the idea of lazy splitting things to the virtual machine stack later when needed. So once we implement that, we are sort of expecting micro benchmarks to be faster than YJIT, but as of now, because we haven't done that yet, that's generally either comparable, almost the same, or just slightly slower than YJIT, which is the current state.
Hi, thanks for the really great talk. It seems like, especially in the Rails context, there's kind of a lot of code that, like you had mentioned with active record, that is kind of pathological, that does things like defeating polymorphic inline caching. Do you think that there's a role of extending the Ruby language to almost disable some features? I know earlier in the session we had Carbon, and a lot of that was kind of being able to roll back features from C++ in order to make it more memory safe. Is there a role of a restricted Ruby language that restricts things like the dynamism that you pointed out before, specifically for those small, very hot areas, such that you could get a more reliable performance from those?
Even the the language author Mats considered such kind of design as well, but there's an issue with that. So like, for example, even if you remove the binding feature, for example, like that allows you to access local variables, it just costs us some memory because like we could still invalidate the local variable access by having the invalidation point, and then when the binding method is called, we can invalidate such kind of things. And for the megaconfig call sites you mentioned, I think it's sort of a very core feature of Ruby. Like if you can't duck type the classes, then kind of loses the point of object-oriented programming. So because Mats is kind of in favor of the programmer happiness in general, I don't think that particular, like the megamorphic call site part is not going to be solved. So I think we still have to like fix the problems by ourselves. And also personally, I'm not a fan of like modifying the language for the performance. So like, I think I still believe in Ruby could be pretty fast without modifying the language semantics. So I still want to keep optimizing that until hitting the wall. That's absolutely not impossible to optimize. So right now, I think we should just duplicate the body of the megaconfig call sites, and then that should, I think that there's a problem.
Great, thank you.
Thanks. I think we are running a little bit out of time, but okay, last question.
You were saying GC on that benchmark was 15% of the time. What does that mean? Like, what is your GC architecture? Are you guys like actually like every int is an object in Ruby? Are you actually allocating an int object every time an int is used, stuff like that?
So we have, despite the semantics being the object-oriented language, there's still immediate like implementations for some types. For example, integers have a fixed num representation that doesn't need to be heap allocated. So for example, the 1 plus 2 doesn't allocate anything. The GC time spent here is like, this is the Linux perf script integrated with the Linux perf, and then we sort of analyze the use of time spent in C functions based on the name of the function. And then this GC category is based on either the name has a lock or free, or ZC underscore something. So like allocation and free, and also the GC mark and sweep are included in this category. So
is your GC stop the world?
No, it's an incremental marking, and so generally, if the minor GC runs, it doesn't spend a lot of time. And in this Ruby benchmark, we've seen basically no major GC in the benchmark applications. We sometimes see the major in the boom applications, but that's not part of the benchmarks generally.
Is it concurrent or?
Not concurrent.
Got it.
Okay, thanks a lot.
The story of how multi-core OCaml went from an idea to an actual thing that we could use in production. And in part, what I want to talk about is the kind of particular technical things that we learned along the way as we kind of went through this process of trying to productionize this work here. And in part, talk about the kind of broader story of technology transfer, of like what it takes to take an idea and a good set of work that's been done in an academic context and move that into a large-scale industrial production use, and the things that you learn along the way doing that. And I want to start with a paper, right? Appropriately, here we are at, I guess, a mix of ICFP and UPSLA, and there was a nice paper in ICFP in 2020 called Retrofitting Parallelism onto OCaml that really kind of went through this whole like design and set of ideas. And the goals of the paper were to produce a modern, high-performance, multi-core garbage collector that would fit into the OCaml ecosystem. And critically, the idea is that this design should be both easy to maintain and easy to adopt, easy for people who were using the pre-multi-core OCaml to pick it up and have it work for them. So on the subject of maintainability, part of the design here was to have only one runtime to maintain. Programming languages are outrageously expensive to maintain. Every part of them is very expensive. There's a lot of engineering and work that goes into each and every one of these. And having just a single runtime that would work for both parallel and sequential workloads was part of what they wanted to achieve. And to make it easy for people to adopt, they needed to preserve sequential performance. So you could take your program that was written before multi-core and use it on the multi-core GC, and it should still perform pretty well. And not just the overall performance, but also the pause times induced by the garbage collector. This is really important if you want to be able to write good, soft, real-time applications to kind of preserve the behavior. And in fact, OCaml has an incremental garbage collector. It does a good job of having relatively small pause times, which is good if you want to build soft, real-time applications, which it turns out at Jane Street we do. And also you want to preserve the FFI, if possible, because all the code written against your FFI is already wrong, and then you have to like maintain it and move it to a new FFI with subtly different semantics, and it's going to be an enormous amount of pain and suffering and a source of many bugs. Another thing the paper did is it produced a bunch of benchmarks and evaluations to see whether or not it really met the goals. And if you looked at those evaluations, it looked like something like a few percentage points of loss of performance for sequential programs, which was thought to be a kind of acceptable loss in that case. It's worth saying, you shouldn't talk about the performance of a garbage collector as a single number. Garbage collectors are really a curve, right? There's a kind of there's a trade-off between space and time, so you need to think about both of them together. But the benchmark showed relatively similar memory usage, also similar pause times, and overall good parallel speed-ups, right? You sort of were able to, in fact, throw multiple cores at problems and have things go faster. So all of that was pretty good. So it did, though, kind of take a while. So yeah, 2013, the project was born. There's a number of papers marked in green that were written. This is not an accidental feature. If you would like to get your fancy new feature accepted into OCaml, you might want to write some papers. So 2015, there was a paper at the OCaml workshop about effect handlers. There's the retrofitting parallelism to OCaml one that I mentioned before, and then another one, retrofitting effect handlers to OCaml, published in 2021. There's this Sandmark benchmark suite that was an important part of figuring out whether they were hitting the performance goals at all. And then in 2020, the upstream team was like, all right, we're doing this. We're going to upstream this thing. We got to actually get it done. And finally, in 2022, OCaml 5 was released. It had multi-core GC and effects, and we're done, right? It's simple to maintain. It's easy to adopt. We're all done. Well, yeah. So then there's another 2.5 years of stuff. And in some sense, this talk is about those 2.5 years and why they're there and what they came from. Some of it's kind of straightforward. If you look at the things in blue, those are all features that had to be backported or forward ported, whatever, brought back after they had been deleted. Because it turns out, we'd been working on the garbage collector. Various improvements had landed during this like long process of generating the new multi-core GC. And so there was this like very cool optimization of adding software prefetching, which it turns out if you do it just right, rather than getting like a 20 to 30% win, which is sort of what you see in the literature, we actually got like 2 to 3x multipliers in speed. So that was kind of awesome. Definitely needed to get that back. Compaction had been not done in the first version, that had to be added in. There was this very cool stat-memprof, statistical memory profiling facility that had to be brought back. But then like there's some other things that happened where we had to like switch to a new runtime, and there was this rather awkward thing of there's a new language, which was different in a number of ways from the old language, with a new runtime. And it's like, well, you should just switch to the new runtime. It's like, no, right? You can't do that because the new runtime is very different. You have to actually have some period of experimentation and seeing whether or not it causes problems. So we did a bunch of work back in 2023 to get what we call OCaml 5 minus. It's like the OCaml 5 language with the old OCaml 4 runtime, and then eventually with the ability to choose between the two runtimes so we could compare their performance. And then we compared their performance and like, we're not happy. Like it turned out there were real performance regressions that like hadn't been clear before. And then there was like a lot of work, and then here we are, 2025, and earlier this year, finally like, it was announced to be at general availability within Jane Street, and we were able to start using it. And kind of the question is like, what happened? Like why did we, both like what did we discover along the way, and like how did we get into this spot? All right, so first of all, I should talk about who did the work. Here I am talking about it, but I have done nothing. But so there was a bunch of the original academic work that was done, and kind of the names on the paper. And then in the last 2.5 years, there was a bunch of people mostly at Jane Street, and with some collaboration with some of the other folk who did the kind of the original work. But like this was kind of the focus of a number of people just like doing a lot of experimentation and work to figure out and understand these problems. So all the work is from them. All the mistakes in presentation are mine. So what I want to do is just start by talking about what is going on, what the differences are between the two versions. I'm going to like, in a number of places, give you like a tour of like what things were like in runtime 4 and what things are like in runtime 5 and how they differ, and then we'll talk about some of the things we discovered. So what is runtime 4 like? First of all, it's sequential. That's what this whole talk is about, right? It used to be sequential, now it's parallel. It's also generational, right? There's the good old generational hypothesis. It's a surprisingly robust finding across many different programming languages that most memory dies young. And on the basis of that, you can have a generational collector where you have a minor heap and a major heap, where the idea is that the minor heap, most of these young allocations will never escape from the minor heap to the major heap. So on the minor heap, you can use a brutally simple allocator. An allocation in OCaml is 3 machine instructions and is very fast. And then when you get to the end of the minor heap, you just kind of copy the survivors, and because of the generational hypothesis, there aren't many survivors, to the major heap. And then the major heap is a kind of traditional mark and sweep collector. And then one additional important piece is in order to be able to collect the minor heap, you kind of need to not have to trace everything to know what is still alive on the minor heap. If you were in a lovely, pure functional programming language with no, dirty mutation or laziness or anything like that, you would have the nice property that everything in the minor heap would have you'd have no pointers from the major heap to the minor heap, right? Because like everything in the minor heap is newer than everything on the major heap, right? And therefore, you'd need mutations to get like arrows going in the wrong directions. But of course, we do have mutations. And so you add a write barrier, which is on the mutations, you check whether it is introducing a back pointer from the major to the minor, and then you're going to track that separately, essentially as an extra route for the traversal of the minor heap to make sure that you can actually detect what is in fact alive. To talk a little bit more about what is a mark and sweep collector, it's a familiar topic, but just to remind everyone, what do? You've got a mark phase and a sweep phase. The mark phase is you start from the roots, and you kind of do a traversal of the whole heap, marking all reachable objects. And then you do a sweep phase where you walk over the heap, collecting all the things that you have now shown to be unreachable. And just to remind everyone what's going on there. Sorry, wrong diagram. So in blue we have the roots, and then we have all these blocks on the heap with arrows between them. And you just start doing a traversal bit by bit, and turning from, as you kind of do the walk through the tree, turning from red to green, basically from unmarked to mark. And as you get to the end of that, then everything that is still red is stuff that you know is gone. So it's the end of the mark phase, and then you get into the sweep phase, and now instead of walking over the object graph, you just walk over all of memory. And like you hit anything that's marked, and you're like, well, that's going to stick around, and next time we're going to have to do this again. So let's make it unmarked. And then every time you see something that is unmarked, you're like, well, that's done, and I'm going to free it, right? And then you just kind of keep on doing that through the rest of the heap, and when you're done with the whole cycle, and you can start again, right? So that's like the basic story of a mark and sweep garbage collector. It's not quite an OCaml quite so simple. That like shows everything happening in one phase. Actually, the OCaml garbage collector is incremental, right? Which is to say, you can break up both the marking and sweeping phases into what are called slices, little bits of work you can do at a time, so you can have the pauses that are imposed be small. There's some extra overhead from doing that, but it makes the resulting system much better for any kind of soft real-time thing. And actually, you need this. It's like insane not to have. You're gonna have like multi-gigabyte heaps and no way of incrementally scanning them. It's just like, you can't build, it's not like, you don't have to be worried about like writing trading systems, like you can't build a UI. It's just like too bad. So the incremental stuff is really important. And then one other important part of the design is the design is built on what's called a snapshot at the beginning invariant, which means when you think, what does it mean for the collector to be correct? What does it have to collect? And the idea is, well, anything that was allocated at the beginning that's unreachable should be collected by the end, right? And the point is you don't necessarily have to collect, you're not obligated to collect things that are allocated along the way. This turns out to be, it's not the only way to build a garbage collector, but it's a useful invariant because it means that you kind of have a bound on how long it is going to take for the collector to get to the end and finish and actually collect things. Of course, you only actually do the freeing when you get to the end of the cycle. Right? All right, so that's runtime 4. Let's talk about runtime 5. And maybe the first thing to know about runtime 5 is it's a lot like runtime 4. Many of the properties are preserved, but it changes in some important ways. Maybe most importantly, parallel, right? It's now a parallel collector. And in order to make that parallelism work, there are, part of the story here is there's some stop the world phases, some spots in the collection algorithm where all of the different threads that are running have to coordinate and kind of hit a barrier in order to kind of make progress from there. And then in order to make that work in an adequately performant way, there are safe points, right? You have to make sure to insert spots into every program which will stop and check in with a garbage collector. So among other things, it can actually participate in these barriers, right? If some thread kind of can't get to the point of getting to the barrier, the whole system gets slowed down. And you basically do things like add a safe point at the back edge of loops and things like that. But you want to make sure that like reasonably often you're going to have these safe points that interrupt the running of the GC. Again, we have a minor heap, but actually minor heaps, multiple, one minor heap per thread, per core that you have. And in the minor heaps, we're going to do a stop the world collection. So all the minor heaps, this is one of these kind of stop the world phases, all the minor heaps are going to collect together. Notably, like some might finish earlier, like different threads might be allocating different amounts. So the ones that finish early just like spend some extra time collecting the major heaps so they don't waste their time, but they really do all have to get to the end in order to move on. And then we have the major heap. And the minor heap is basically not shared, right? It is meant to be separate, one per domain, and the reason for that is to avoid the costs of synchronizing a bunch on those, because you want to make the minor allocations as fast as possible. But all the shared stuff ends up going into the major heap. And an interesting detail of this is they ended up with a merged mark sweep design. So instead of having a mark phase and a sweep phase, there's like a sweep and mark phase. And this design idea was stolen from the very concurrent garbage collector. And the idea is, well, these synchronizations, those sound expensive. Let's have fewer of them. And so by merging the two together, you get to have one less synchronization point. Right, and again, at the end of that, there's a little stop the world synchronization kind of at the end of the merged mark sweep cycle, but just one. So let's talk a little bit about, we sort of talked at a high level, let's kind of remind ourselves how this whole GC color thing works, right? The colors are these like little state bits that we have that we kind of manipulate as we wander around. So in runtime 4, there's a marking phase when you move unmarked blocks to being marked blocks. And then there's a sweeping phase where unmarked blocks are made free and marked blocks are made unmarked. Okay? Runtime 5 is different. There's a marking phase, or rather there's marking activity. There's not phases, right? Sometimes you're doing marking, sometimes you're doing sweeping. When you're marking, you're moving unmarked to mark. When you're sweeping, you're moving garbage to free. So there's an extra color, there's an extra identifier, right? Some things are explicitly marked as garbage. And so there's like something obviously nice about this, which is to say you can just kind of tell from looking at these transition diagrams that you can intermix the marking and the sweeping because they're not touching the same colors. So they're kind of not going to interfere with each other. But that's also bad, right? Because you actually need things to move from being marked to later being swept. So somehow you have to like tie the knot. And that's what the thing that happens at the cycle end is, right? Which is you have this cycle where you want to take all the unmarked things and make them garbage, and all the garbage and make it marked, and all the marked and make it unmarked. But instead of, like in the previous diagram, doing this by walking through and changing the colors, you just, the colors are just a state of mind. You basically like have a constant amount of space that tells you like which bit pattern means which thing, and you just like atomically switch it, and like in some sense the meaning of all the bit patterns changes, and you don't change the physical bit patterns, but the one that used to mean unmarked now means garbage, the one that used to mean garbage means marked, and so on and so forth. So let me just pause for a moment, because I've said like a lot of things about the garbage collectors. Like, are there any questions about like the details of like, there's a lot of details. You can understand various pieces of this without maybe understanding all of them, but like anything anyone is like confused about, or there's some of the people who worked on this paper, they can tell me I'm wrong. Like, is there any? All right.
I understand right that's at the moment where you like change your At the moment where you change your interpretation from interpreting some bits as like meaning garbage to meaning marked, there's nothing that actually has those exact bits?
Oh no. No, there are things that have those bits, right? But the whole point is it's like the thing you semantically want to do is you want to like recolor things, but you kind of do it atomically for the entire set of things by just kind of locking the place where the interpretation is stored and changing the interpretation. But yeah, you've kind of gone through this phase, and there were things that were unmarked, and you put them as marked, and now those things that are marked, you want them to be unmarked for the next cycle, and yeah, it changes them, so they are now unmarked for the next cycle.
Oh, sorry, what I mean is like specifically for garbage, you've like freed everything that was marked as garbage. So
yes, that's right. So the garbage one in particular is gone. So it's like we are just moving that one because we want to use the bit pattern, but that one there are no things that actually need to be in that stage.
Thanks.
Yeah.
I've forgotten how it works in OCaml. How do you know what's shared and not shared? Like, how do objects become in the part of the shared heap?
Right. So, and this is like a thing that I actually don't really remember. That there's probably people in the audience who will do a better job of this. But there's like a kind of discipline where you basically detect dynamically that some things are shared and can promote them to the major heap.
Sorry, a thing Ron didn't mention is the first paper had 2 different garbage collectors in it, and he's just quoted something from the wrong one.
Aren't there? But if you mutate them, don't you have to move them? I thought there was a stage where you did have. No, now there's just no moving. Got it.
You don't have to change it after 5 of them.
Right. Yeah, it's good to have the actual experts in the audience. All right. Okay. So now let's talk about what went wrong. So remember I said you need to think about the curve of the performance of a garbage collector. It might be better in CPU terms and worse in memory usage, or the other way around. This one was worse in both. So we found some programs were like 10 to 20% slower, and for those of you who are paying attention closely, that's more than 3%. And then also, excitingly, some programs were using 10 to 20% more memory. And actually, these were like things we saw in some early benchmarks, but like you could come up with benchmarks that were much worse, right, in various things. So that was like distressing. Like this was like not the shape of a thing that we could in fact roll. And it's clear, some programs, there was like variation between the different programs that you ran. Some were affected a lot, some not very much. And where did this come from? And there's like a much longer version of this talk I could do. I mean, I could do if I was more competent. So maybe like we could collectively do a several-hour version of this, of like going through all the different things that were discovered and how we did. But like just to give a high-level summary of things that we found. So first of all, there were some problems in pacing in the GC that were subtly different between the two collectors that we had to work through. There was also like a long, kind of hilarious sequence of problems with transparent huge pages, where, you know, the old garbage collector had been invented before huge pages. You say, what are huge pages, right? In the 1970s, when God invented Unix, right, pages were 4K, and we were all going to be happy with that, except hardware changed a lot, and 4K is an insanely small page size. So there are these larger pages, 2 megabytes, but like rather than like switching the system to it in some kind of general way, there's like a bunch of clever stuff in the OS to automatically allocate for you these kind of agglomerated huge pages instead that are 2 gigabytes typically. And like, you know, Stephen Dolan can tell you a bunch of stories about how broken this has been for many years in the Linux kernel, where like that system for doing it was like kind of awful for a very long time. But anyway, the original garbage collector was designed before there were transparent huge pages, and therefore worked very well with it. And the new garbage collector was designed after there were transparent huge pages, and therefore worked very poorly with it. Anyway, there's a whole complicated story about how that happened, which I won't go into, but that's one of the fun things we hit. There was also just like, there's the new parallelism that we have with domains, and the old parallelism with sys threads, and like, they were integrated in not quite the right way, and there was a bunch of like annoying extra overhead there that we discovered. Also, there's this like heavyweight domain thing. We also have a new lightweight thread notion. Then this kind of threadlet thing had its own notion of stacks, which were different from the old stacks. And there are checks to know whether you've gotten over the edge of the stack. And like the new ones were kind of slow. That was another issue that we ran into. And just generally, like parts of the code were not as fast, right? Like the old code had like, you know, been beaten into shape over a long period of time. And there were just like places where it wasn't engineered as well as possible. So I'm not going to like go over like this entire list and talk about it because it's a lot. I mostly want to talk about the pacing. There's like an interesting story there about we learned about GC pacing, and it's kind of enough to give an illustration of the kind of things we were doing and learning from here. So let's talk about pacing and how it worked in runtime 4 and then how it works in runtime 5. So on this, there's kind of two kinds of memory we're going to talk about. There's memory allocated on the sort of ordinary garbage collected heap, and then it turns out we sometimes care about off-heap memory. So we'll talk about both of those. The approaches are pretty different. On-heap memory, well, there's a question of, I said there's that curve, right, about like how you trade off space for time. You have to decide how you're going to configure your system to make that trade-off. And there are different ways. Like classic garbage collector papers are all about Java, and Java, you know, hulking enterprise Java had like a hulking enterprise model for doing this, and you have like a roofline model, meaning like you're going to run your Java program in a box, just one program, right? And it's going to use the whole box. So just like tell it how much memory you have, and it will trade off space with time to avoid exceeding that total memory. That is not what OCaml did, and it's kind of not great for like how we use OCaml for like a lot of stuff. Sometimes for like big hulking enterprise program that takes over a whole box, and sometimes for a million little programs that do a lot of different things. And so instead of trying to configure it in this roofline model, there's this notion of space overhead. You just ask, you know, how much extra wastage in percentage terms are you willing to tolerate, and that's what we're going to target. So that's the basic tuning idea. And the way this is done is based on what's called a steady state assumption. So what you're going to do is like think back in your armchairs, like how might this work? I'm running a program. Let's say I'm running it for a long time. How much might it be collecting? How much does it need to collect? Well, it's like, well, if it's running for a long time, like it can't use an infinite amount of memory. So like the amount it's collecting has to be basically the amount it's allocating. So we could like just make the assumption that we need to like collect as much as we're allocating. And then all that separates us from a way of doing the pacing is some high school algebra. We can just like set up some equations and work it out and like come up with a number. And that's basically what happens. It turns out, in a lovely way, you do the high school algebra and like stuff cancels out satisfyingly, and you discover that you can just do a constant amount of collection, some marking and some sweeping, which you can sort of measure in like number of bytes you have to mark or sweep versus number of bytes you allocated, per word promoted, right? So remember, there are like two parts of the garbage collector. There's like the minor allocations, but the ones that matter for clocking the major heap are promotions to the major heap. We kind of don't care about the minor heap when we're thinking about the major heap. Okay, so that's how that part works. And now what about off-heap memory? So first of all, what do I mean off-heap memory? So for various reasons, you want to kind of take responsibility for memory that is not managed in the ordinary way of camel. Maybe it's because you're doing I/O and you want like regions of memory that aren't going to get moved around. Or maybe you're using some third-party library and you want your like PyTorch tensors or your like GMP numbers or whatever to be taken care of like off the heap because you don't have control over those. Like there's just some other library you're interfacing with that's actually responsible for that. But kind of the garbage collector is responsible for collecting those because the way you do it is you like have a garbage collected value that's a points to that's responsible for the off-heap memory, and then when that gets collected, well then you're going to like do the free to get rid of that stuff that's off-heap. So the garbage collector really is responsible for and needs to be clocked in part by the need to collect the off-heap stuff. So what are we going to do? Well, here's what we did, or what the long ago Damien Doliger did. There's an extra, just a number called extra heap resources. Think of it as a number that goes from 0 to 1, and we're going to use this number to determine when we have like a whole extra cycle worth of work to do. So we're going to increment this extra heap resources by this little n over kh equation every time we do an allocation. So n is like the amount allocated by that allocation. H is the overall size of the garbage collected heap, and k is like some constant to like, which is going to tell you how fast you should be going. And like the kind of rough intuition about how this, like why this kind of makes sense is like, if you have like an amount of extra stuff roughly proportional to the amount on the heap, then you kind of want to collect the whole heap, right? Like that sort of incentivizes you at kind of roughly that ratio. And if you want like a better, more principled argument as to why this is a good idea, I'm going to disappoint you because there isn't one, and it turns out it's not a good idea. But anyway, it's what we did, right? Okay, so this all makes me want to talk a little bit about control theory, right? Because like, what do we got here? We've got a system where we are trying to like control some process by kind of making measurements in the world and deciding how fast to work to kind of keep some dynamic system in control. And when you build these kind of systems, it's worth distinguishing between open loop and closed loop control. So what do I mean by that? So an open loop control system is one where you observe something about the world and those drive some set of decisions that you make. But the decisions you make do not affect the quantities that you're observing, right? It's an open loop. You just like make decisions based on what you see. So why might you like an open loop system? Well, they're like kind of predictable and easy to manage, but a big problem with them is they don't necessarily do what you want to do, right? Like in some sense you are aiming towards a target, you're trying to modify, you're trying to move a target, and because you're trying to modify it, if you want to be open loop, you can't look at the thing you're trying to modify. That's what it means to be open loop. So a kind of a little more predictable, but like harder to like get to do exactly what you want to do. And there are closed loop systems. In a closed loop system, well, it's just like the opposite. You get to observe the quantity that you are trying to target for. So what's good about these is you can really zero in exactly on the target. And what's bad is like, I don't know if you've ever done like high school robotics, but you're now in like PID controller hell. It's like, you gotta like tune the parameters, and if you're like too aggressive, you end up like oscillating back and forth as you try to get there. And if you're unaggressive enough, it takes a long time to converge, and it's just kind of no fun, right? So, and if you look back at the design we talked about, the heap pacing turns out to be open loop, right? Delightfully, terms like the size of the heap just kind of canceled out in our high school algebra. It's a lot of high school algebra, high school robotics, anyway. But the off-heap pacing is closed loop, because we're looking at that capital H. Like that's a quantity that we're controlling and we're responding to. Okay, so this will matter later, but I just want to like lay those ideas out there. Now let's talk about the results. Like how did this thing work in like runtime 4? So first of all, I just want to like lay out what this graph is supposed to show. There's no data here yet, but on the x-axis we have the the space overhead we requested, right? So like 100 in this graph means I think you can like you can up to have like up to a factor of 2 extra memory. And then we can measure like what's the space overhead we got, right? And then what do those lines look like? So it turns out they look like this. So there are 3 different lines. The ones that are like kind of close to the black line are benchmarks where we're like allocating a lot of lists or we're allocating like a bunch of strings. And you know, there's some interesting stuff going on there. There's like some like weird like stair step thing going on, and that's mostly because the system has like it doesn't like grow the heap in little bits. It grows the heap in big chunks. It turns out. And so that's it, but it's like pretty close. It's sort of doing approximately the right thing. Our control equations seem like they're like not terrible predictions of real life. And then there's that horrifying line on the bottom, and that's a benchmark which is really, really aggressively allocating external memory, these big arrays. And there what you see is like it's just not responding to the control thing at all, and the garbage collector is working super hard all the time to collect as much as it can, right? So parts of this work well, parts of it are horrifically broken. And it's worth saying, this is runtime 4. They were horrifically broken before we started, and this is a real serious problem. Like we have spent at Jane Street like quite a lot of time wrestling with bad garbage collector behavior, specifically around this external memory, and have tried over the years various different kind of hacks to improve the behavior of the GC to fix this, and not being enormously successful in that. All right, so that's how runtime 5 looks when you use it. How does runtime 5 look? Well, so for ordinary on-heap allocations, the pacing story is basically the same basic equations. But you know, here we are in the garbage collector. We like looked at things and like we fixed some stuff. There were some bugs actually in the original implementation. Notably, one of the fun bugs was instead of clocking the decisions about external memory were made for every allocated block, not for every allocated block that's on the major heap. So like that benchmark that's very, very aggressively allocating big arrays, like most of them are disappearing on the minor heap and never getting to the major heap. You shouldn't be doing any collection on the major heap for those. They just don't matter, but it does it anyway. So that was like, and we fixed that and a few other bugs in the implementation. I should also mention every time I say we, I did none of this work, but the royal we did this work. And then now we can see, okay, what are the results of that? How does runtime 5 actually look in practice? And it's like not what we wanted. This is not good behavior. So like the byte and list allocations are like screaming up high, so they're using way more memory than they should be. And then there's like the external memory, which looks like a little better, I guess. It's like, it's not nearly as aggressive basically because we fixed that thing with the kind of minor heap stuff, but it's still like not responding at all linearly to the control thing. So this is like, this is not going well, right? And this is like, you try to roll this into production and like bad things will happen. Like things that ran yesterday will like and crash and stuff. So this is like. That's right, yes. That's right. As Leo points out, this is not like a theoretical, it would have been bad. It was bad. We did it in production and it didn't go well and rolled it back. Okay, so we're like, oh, this is not good. What are we going to do about this? I don't know. Lots of things go wrong at small scales. I don't. So what happened? So first of all, it turns out ordinary collection was just less aggressive in the new GC than in the old GC in a way that like we kind of knew but hadn't like been totally thinking about. Like the people who wrote the paper were not unaware of this change in the design, but like it was just kind of a bigger effect than people were quite like counting on and thinking about. So just to illustrate what's going on here. So, you know, here we are talking about garbage collection. So my graph doesn't show, like, there's the interesting part of the system, which is the garbage collector, and then there's the mutator. It's like that user program that nobody cares about, right? We're just here to talk about garbage collection. So I don't even picture the mutator on here. This is just the garbage collection phases, right? So in runtime 4, you have these like sequence, you know, sweep mark, sweep mark, sweep mark, and then you think like, if I allocate something, how long does it stay alive for? So if I allocate something in the middle of the sweep phase, well, it's It's not going to get collected in the sweep phase. In the mark phase, by the end of the mark phase, you're going to know it has to be freed. And then by the time you get to the middle of the sweep phase, somewhere in there, you're going to collect it. So you basically wait kind of one full cycle's worth of time to collect something that was allocated, at some random point in the sweep phase. If you allocate something in the mark phase, well, because of the snapshot at the beginning thing, it's not going to get collected in that mark phase. It's not even going to get marked by the end of that mark phase. It's going to get marked at the next mark phase, and then only swept up at the sweep that follows that. So we're going to take 1.5 cycles for that. So like basically 1 1/4 cycles is like how long you're going to have floating garbage, right? Things that have been allocated and aren't yet collected, even though they could be. So what about the merged kind of VCGC, very concurrent garbage collector style system? So here again we have these merged sweep mark phases, but like it's worth saying it's not like totally uniformly distributed sweep and mark. You like mostly sweep in the beginning and mostly mark at the end, and the edges can be a little blurry because you haven't synchronized. So we can kind of again ask the question of like, if we allocate in the beginning of the sweep, what happens? Well, it has to get to the end of a full marking phase, and then to like the middle of the sweep phase of the next merged phase after that. So that's going to take 2 full cycles to get collected. And if you allocate something in the middle of like the marky part of the sweep mark phase, well, that's actually going to take 1.5 cycles. So that 1.5 is kind of the same as before, but the allocated in the middle of the sweep phase is a lot worse. So it like went from 1 1/4 to 1.75, and that's a big change to how fast the collector is running.
Stupid question when you say, stupid question when you say allocate, you actually mean forget, right, or drop.
Sorry, yeah, that's right. I guess a thing that it's really like a thing that becomes ready to be collected. That's right. That's a better way of saying it. All right. Okay, does this picture roughly make sense to people? All right. So that was a problem. And then we decided to fix that by basically saying, you know what, that part of the VCGC thing, like, maybe that was just a mistake. Like, we just broke them up into separate phases, 1 extra synchronization. Actually, one thing we kind of learned along the way is like the synchronizations we were worried about is like actually kind of cheap. They're actually not that expensive. Having an extra one is not so bad. And like they kind of scale pretty well. Like roughly you should expect them to like grow in cost with the like log of the number of concurrent domains you're running. So it's like at the scales we're talking about, just kind of not that big of a deal to add 1 extra, and it makes making the collection much more aggressive is just worth a lot, because otherwise you have to do a lot more GC in order to make things happen. So as I said, the excessive collection with big strings is better because we fixed that bug. And that bug fix like made the allocation less aggressive, which made it better. But it's worth noting there were others that made it more aggressive. And like a general theme of this work is like, there are a bunch of things that are wrong, some of them offsetting. And then people are depending on it. And like at this point, the bugs are load bearing, right? The entire ecosystem has adjusted to the behavior of the system. And when you change it, even in ways that are good, like some things might not go well, and especially when you change it in bad ways. So it's just like a complicated place to engineer. All right, so we did this mark delay patch. What do things look like now? Better-ish, right? Some things are like, the green lines are still not that close to the black line. They're still like curving somewhat uncomfortably away. The bottom green line for the off-heat memory thing is like worse now because we've made, mark delay has now made things more aggressive. So this is now more extra fast than you want it to be. So we're still like pretty unhappy at the state of things. Like we fixed stuff kind of, but like the world is not in a good place. So what do we do now? Well, we're like, okay, look. We tried to fix some of the implementation bugs before. Maybe we should fix some of the design bugs. And in particular, one thing that was noticed is like this like n over kh equation was kind of wrong. Like the h was the wrong h. It was it was like the amount of memory in the garbage collected heap. But you kind of want to, it makes more sense to think of like the kind of memory in the overall heap. That seemed like, again, there's no good principle argument for why this is exactly right, but that seemed like a step in the right direction. Like the really pathological case was where this ratio was super high, where you're like, you have lots of off-heap memory and very little on-heap memory, and then you just like insanely want to allocate over all the time, even though actually there's very little to walk. So you're just like constantly walking this tiny heap, and it just makes no sense, so we thought we could fix that. But like this wasn't great either because now we're like in a world where we're dealing with this like closed loop control system, and it's again like hard to get right and hard to tune in the right direction. So what did we do? We basically took the last possible resort and decided to think deeply about the problem, and in particular be like, well, maybe like this n over kh thing, like, did that make any sense? Like, why did we do that thing? And like, people went back to the like, what actually would make sense from a more fundamental perspective, and let's like think a little more precisely about how the garbage collector really works, try and get the high school algebra a little more right, and go back and rethink the steady state analysis. And like, kind of to everyone's surprise, there was a really nice solution, and it was an open loop solution for both parts, which I just want to emphasize, we know no good reason why this had to be true. It's just like the math kind of worked out, things canceled, and like you ended up with a nice solution. And it doesn't, I mean, it kind of makes sense. Like you ended up with constant number of words collected per word allocated. But notably, there's an extra word of sweeping when something is on heap, which kind of makes sense because you don't actually need to sweep the off heap stuff, right? So like, there was no quite reason for it to work out this nicely, but also like the end result is like kind of coherent. And then we tried it. What does it look like? And like, I'm not sure if I can convey what a feeling of like warm comfort and relaxation I get from those blue lines. Like, they have the right angle, they're relatively close to being on target, right? And some of why this is right is like, yeah, and also like there isn't this like disaster for off-heap memory. It's like it all just kind of works nicely together. And like some of this being more on target is like the fixing of the off-heap thing. Some is just like a little bit more like care and accuracy in understanding like actually how exactly does the garbage collector behave, and like getting the setup of the equations that you then applied the high school algebra to just right. Right? Okay, so this was like a very satisfying end result.
It's so divergent, but is this a happy ending?
Yeah, I think this is a happy ending. It's diverging a little bit, but it's not like curving away. And it's maybe worth saying like, you don't have to get it exactly right. Like, I think part of the observation of why you prefer open loop control to closed loop control is you actually don't care that much if you exactly hit the target, but what you want is a knob that works and works predictably. And even if it's a little off, even if it's off by like, a little, the slope's a little off, like you still get a knob that you can turn. And like that's actually the most important thing that you want out of a system. Okay, so that's like the end of like the deep technical stuff that we were doing. Like what did we learn like at a meta level from this whole process? So one thing is like benchmarking is super hard, like hard to get right. And I think the original testing that like went into the paper just leaned too much on small programs. And it just turns out like different programs put different pressure on the design, and it really matters what things you measure. I think actually there's an interesting like structural thing about how the paper and the original implementation was set up that kind of made this happen, because like what kind of benchmarking you're going to do, the kind of benchmarking that you can practically do, right? And one thing that made benchmarking real serious big programs hard is there was only one runtime, right? Which per thing. So if you wanted to like compare the two runtimes against each other, you had to use two different branches of OCaml with two different languages, right? The language has evolved a little bit. And when you add new features to your language, people start using them. And so we didn't have like a corpus of programs that you could reliably, easily run on both of these. So like part of what Sandmark did was some careful curation of like programs that would work nicely on both systems and kind of keeping them up to date and working in both places. And that's a pain in the ass. Like nobody wants to maintain a big program in that form. And so it like pushed in the direction of less serious performance evaluation. And like, I think it would have been better to not do that and to prioritize more, like understand in the end we have to delete the other runtime, but prioritize more the ability to really do the like-for-like comparison and do it on more serious programs. Another point is that performance debugging is hard. Like, you're going to have a new runtime. It's a complicated system. Many things are going to be wrong. And the different things that are going to be wrong will cover each other up. Like the biggest one makes it hard to see the other ones underneath. And then also fixing the performance problems are wrong. And we made one part of how we did that is we would like look at what the problems were and then build a nice high quality improvement to try and resolve that problem. And that was a mistake. We should have written bad code to solve that problem. What you want to do is like do a bunch of relatively quick experimental ways of seeing whether this thing actually moves the needle, so you can like explore and experiment more quickly rather than putting a lot of polish into a solution for a thing like, oh, that wasn't the problem. That's not exciting. And the other thing is just like, you know, being able to like pin the problem and separate the pieces. We also probably should have done a bunch of more little focused benchmarks that like picked apart the particular misbehaviors so you could understand and analyze them independently and be able to attack them in parallel rather than like in serial solving kind of one after the other. Another observation is like, you know, sometimes you should stop and think, right? I think that like we had just gotten so used to the off-heap thing being bad that like we hadn't thought maybe it could be good and like really spend like a hard thinking effort to go off and like see if we could solve this in a fundamental way. And it turned out in this case, delightfully, that a first principles approach like really solved the problem. And it didn't just solve like, you know, make runtime 5 better, but it like solved problems that had been pre-existing, had been bothering us for like the 20 years prior. Another point is backwards compatibility is hard, right? Every change you do is going to break somebody's workflow. The whole problem of load-bearing bugs just makes it hard to make changes. There's like a lot, it's a big, complicated business with a lot of software behind it. And like, it's just hard to make any kind of changes there. So you just have to be, really careful and thoughtful when you do all of that work. All right, so what's next? How did this paper start? How did this talk start? There's like a good paper that was written with like some good work and idea, and then like a long series of painful hijinks as one discovered problems with that. So we're beginning the cycle again. We have this nice paper, Data Race Freedom a la Mode, which came out, won the Distinguished Paper Award in POPL 2025, which basically talks about the second half of this work. You know, part one, the runtime capability to have parallel programs. Part two, a programming model that doesn't make you want to tear your eyes out, right? And so here, the whole point of this is to use this kind of system of modes that we've developed to give type-level guarantees of data race freedom, so you actually have a way of reliably using this kind of system. And there's a lot of work that we're doing to take this idea and move it into actual production. So there's a lot of propagating type information through our libraries, which is like surprisingly hard and tricky. It's in part hard because like ML has a very rich system for like specifying complex interfaces with functors and the like, and like figuring out how to kind of wire things through that is hard. It's in part hard because frustratingly the type system discovers data races and then you have to fix them. So there's a lot of work that comes from that. Also, like, we've never built high performance concurrent data structures, and we need some, so there's a bunch of effort going into building those. One of the nice things about, we mentioned effects, one of the nice things about the original multi-core design is it puts the scheduling work in user space, right? So you can just write libraries that are schedulers, and there's a lot of interesting things to do in building good user level schedulers that can like do a good job of like adaptively solving problems for you. So you know, one of the like standard problems you have in writing high performance parallel programs, right? Parallel programming is terrible, right? It's terrible because data races are hard to avoid. It's terrible because it's hard to pick the granularity of the jobs that you want. You make it too fine-grained and you're swallowed in overhead. You make it too coarse-grained and you can't take advantage of parallelism. So that's like an annoying problem. It's also hard to know like how many threads you can use concurrently. And so there's a bunch of work that we're doing to try and like, you know, some more like, you know, adaptive control theory kind of stuff and clever implementation techniques to make it so that people can write relatively simple straight ahead programs that's like, please parallelize my stuff and have something reasonable happen. Another thing that's terrible about writing parallel programs is they are really hard to understand. We have a, you know, there's shared memory parallelism. No, there isn't. There's like some weird message passing thing which is like dressed up as shared memory parallelism. You're shearing cache lines left and right, and it's very hard to understand what's going on. And so like one of the things you want to do is have reasonable profiling and analysis tools that give you insights so like programmers can figure out why their programs are slow and fix them. Also, you know, there's both parallelism and concurrency, right? You can think of parallelism as when you have a bunch of stuff that you could do in parallel and you're offering up to the scheduler the opportunity to run those things in parallel. There's also concurrency, where you have a bunch of things that you want to demand will not block each other. They can run independently. So in one case, you're offering up parallelism, you're happy if it's taken up. In the other, it's kind of the dual. You're offering up independence that you demand of the scheduler gives you. So these are like pretty different things. It's in fact tricky to build nice abstractions and nice runtime facilities that let you combine them. So there's a bunch of work on that. And then of course we have, a couple thousand people who would like to use this system and need to be taught how to use it. So there's a whole big teaching effort that we are like trying to do, in part by like explicit teaching. We're actually looking to hire someone to actually focus on the teaching aspect, if you know any names. And also just trying to like build the system to give people good feedback to help the tools teach people what's going on. So there's an enormous amount of work there. So stay tuned. Maybe in a few years we'll have a nice talk about how much dramatically harder this was than we expected and various mistakes that we made and why it went terribly wrong. And if you'd like to watch the car crash in progress, we have taken all of this code and put it up and shared it on the internet where people can use it. So the OxCaml has basically the full set of extensions to OCaml that we have developed internally. And it's in an interesting spot. It's like totally a production quality system. It is our production system. Every day, all of our stuff is running on this. When things go well, we release a new compiler every week or two. And like, there's a ton of stuff constantly going there, and like we kind of regularly kind of push this to the outside world. But it's not like exactly intended for other people's production use, because we are going to change stuff mercilessly fast, and like we're not going to help you keep up, right? This is like a kind of compiler where we're like very excited to have, researchers and enthusiasts and stuff dive in and try and help us and like develop things there. But like, I don't know that I would recommend like betting your like very large company code base on this, because like we have control over our code base. When we want to change a thing, we will spend a bunch of effort and like write a mechanical refactor and like smash our 80 million line code base to behave in the way that we want. But those tools do not work on the outside, and we cannot like reasonably share them with other people. And so I think it's not the kind of system that you want to use at scale. I think like the primary purpose of all of this is like, this is a place where we can put these out and get feedback, and like over time, as these things stabilize, we hope to basically upstream all of this to the upstream OCaml compiler. Obviously, we have to like convince people that it's good. It's worth saying it's not good now. Like it's complicated and messy. Like we've done a lot. It's valuable. Like it's worth it. But like the language is not in what we think of as a final state where like a lot of these language features are ready and stable enough to be upstreamed. But we expect to get there. I think the multi-core OCaml process took years. I think we expect this process to take years as well. Hopefully fewer. But yeah, I think we think it's like a fertile ground for connection to other people and researchers and people who kind of want to investigate. And we are like, contrary to our usual behavior, it's like documented, like, pages describing how the type system extensions work and all that. So hopefully it's like even if it's not a thing you want to, run your next startup on, hopefully it's a system that is a fun and pleasant thing to experiment with and try out and to learn from. And we actually think there's like a lot of fun and interesting ideas here that like, even if you don't care about OxCaml per se, I think are probably relevant to lots of other languages out there that people are working on. All right, and that I think is all I got.
So it seems like you have solved the pacing problem, because your talk pacing was excellent. So we have at least 5 minutes for questions.
I really enjoyed that. If there's one thing we've learned from machine learning, it's that they have this culture of dynamic benchmarks. So they're always updating benchmarks, having competitions and so on, like Kaggle. And then they've also got this culture of sharing and remixing, right? So they release models and then they run them with these benchmarks. But looking at your timeline, we did a bunch of fixed effort for Sandmark. It was really, really thankless. And then it's pretty much unmaintained now, and you've got your own internal benchmark suites. Should we be treating benchmark engineering as a first-class thing we do in language design? So why aren't there 100 different variations of the garbage collector? We've got one from KC that we heard about in this workshop, but they really are a rare thing, right? So should we really be having dozens running dynamically with people contributing benchmarks and having a bit of a competition all the time? This feels like an asymptotic way to speed things up.
So I think making benchmarks better is good. I think it's also hard. And I think in this case, like I think the first order lesson is not we needed a much, bigger community of people. I think the big lesson is really we should have designed the system in a way that made using real programs easier. Like you could have seen these, and we did see these slowdowns on like sufficiently large runs of like OCaml C, right? So I think these problems, in fact, were relatively coarse-grained and relatively easy to find. Not all of them, but a lot. But there was a lot of pretty big things that I think like the kind of like fine-grained sandmark approach just wasn't going to get, and that we mostly just needed more real programs. And I do think like we do have like a decent number of like open source real programs out there, and I think that some amount of, at least especially for these kind of coarse-grained things, if you're trying to do like really fine-grained optimization, benchmarks are super hard, and even internally at Jane Street, like in many ways we're kind of giving up. Like there's lots of places where people have built nice little benchmarks, but if you're trying to see is that like a 2% regression or a 3% regression, like often we're just we're moving in the direction of more instrumenting production and being able to like run production against multiple compilers and see, you know, randomize which one's doing what and see, you know, over kind of rolling out over time what the problems are. So I think depending on what your goals are for the benchmarking, I think you want to approach things different ways, but I certainly think we could like do better of having a public set of benchmarking that had more large-scale real-world tasks that would, I think, help us catch pretty easily coarse-grained issues. The fine-grained issues are like a deep problem that I mostly don't know how to really solve.
Yeah. So I was wondering if you could talk a little bit about managing this sort of software project, because while you are developing a completely new garbage collector, right, the world keeps moving outside, and you do need to keep what you're doing now up to date with, so that it can be merged in at some point, and like when you have to go back and rethink the thing, redesign the thing, and all of that stuff. Whenever I've been involved in those types of things, it's a pain to keep it on track, to keep it, you know, aligned with what all the systems that it has to work with.
I think that's a better question to ask the next time Casey gives a talk about this. Like this is like the whole hard work of landing multi-core OCaml. Like that's not what this is about. I didn't see that happened off in the background at, you know, at various OCaml labs and the like, and like we were very happy about the result, but we mostly didn't do it. In the future, we're going to try to land a bunch of stuff upstream. We'll see how that goes. It is saying like we do on our world. There is a bunch of work of like, you know, keeping up with, you know, even with our own branch, we want to keep up with upstream OCaml and like being able to rebase efficiently, thinking about, you know, if there are things that are very conflicty, then you want to like push towards upstreaming those pieces earlier. So I don't know, there's various things that we can do on the margin to make it a little easier, but mostly it's just hard work, is my sense.
So, yeah, I mean, you mentioned the sort of mammoth task of merging multi-core OCaml into, I mean, the thing that KC did, merging that into OCaml. I think you have there's a slightly different situation here, where at least, I mean, there were so many moving parts there, like changing to a concurrent garbage collector, deparallelism, effect handlers. For this, at least, that first 7-year part maybe doesn't have to happen.
I mean, I guess I gotta say the challenges of this work are different.
But do you still think it's going to be? I mean, when you said 7 years, this is 10 years, isn't it?
That's fair. So I think, what do I think about this? So, first of all, we should upstream some things earlier. For example, a large fraction of this work on improving the pacing has already been upstreamed. The remainder of it is going to be upstreamed, right? And there are various pieces of our extension. So for example, polymorphic parameters and labeled tuples and various other things like that have already been upstreamed. I think the mode stuff, which is like the most important thing that kind of is driving this parallelism thing, is like it's still like, I don't know, 18 months from being worth upstreaming. It's just like it's just kind of bad in some sense, right? Like we don't maybe like the primary example of a thing that's like quite bad now is we don't have enough polymorphism in various parts of the system, and so we have like a horrifying like templating system that like allows us to programmatically like cut and paste many copies of the same function for different ways, and like we've got to fix that stuff before upstreaming it.
So in some ways that's actually worse, because there's to a certain degree there's a research problem there that needs to be solved in order to.
So yeah, there are some things that are research
But-
problems. There
but
are some things
my-
that are just engineering problems.
But my point, though, is that on the other hand, it's a much easier thing because you're not affecting like the entire infrastructure of the compiler. You don't have to write a new GC in order to get that working. You just need to get the front end done. So maybe this will be quicker.
Yeah, I mean, I think, what do I think? I guess I'll say the actual work of making it work well is like hard work. And it's our experience thus far is it takes real time to do. And so I think, I don't know, I agree that like you don't have the same kind of like uncertainty around runtime behavior. And in many ways, I think there's some of the problems here are going to be social, right? Like, if you ask me what we're building, I think OxCaml is like the analytic continuation of OCaml. It's like what OCaml wants to be when it grows up. It's like the natural set of features. You know, at least the thing we're aiming for now, it's kind of, grotty in spots, but like, we're trying to do something that feels to us like a very natural extension of language in the way that it achieves key features. Like, OCaml is in some sense obviously in an uncomfortable state of it has the ability to run multi-core stuff, and it has no acceptable programming model. Like, if we've learned anything from the process of trying to like push the data race freedom through is like reasoning about data races is subtle and they are not where you expect them to be, and having a nice type system discipline is good, and I think it's very hard to do it without. So I think in some sense OCaml really needs this to like fulfill the promise of the things that have already been built into it. But you do have to convince people it's good. Me saying fancy things about how much I like it is like not going to cut a lot of ice. Like, people have to see it being good. And I think it takes time to make make the type system stuff really effective.
So unfortunately, we are at time, and this is the last talk of Rebase. So thanks everybody for coming, and thanks Ron for your talk.